We are gathered here today at the Visvesvaraya National Institute of Technology, Nagpur for the inaugural function of prestigious Global Initiative of Academic Networks GIAN course on Advances in Engineering Design, Energy Transition and Project Development. I am Anjali and it is indeed an honor to be part of this special event that brings together some of the brightest minds and esteemed professionals in the field of engineering. This course promises to inspire, educate and open new pathways for innovation in the constantly evolving discipline. It is my privilege to extend a heartfelt welcome to esteemed dignitaries gracing today's occasion. Let me introduce each one of our distinguished guests. Please join me in welcoming our chief guest, Dr. Swatantra Kumar Shrivastava. Dr. Shrivastava is an esteemed foreign faculty holding a doctorate in engineering and currently working in Liquide Global ENC Solution Germany. His extensive expertise and global perspective in engineering make him truly inspiring figure for today's event. I would like to appreciate the presence of Professor Prem Lal Patel sir, Honorable Director of VNI. To serve as a patron for this course, his leadership has been a guiding force behind this event. We are also deeply honored to have with us our guest of honor, Professor K.M. Shende sir, GIAN Activity Founding Institute Coordinator and currently the Dean of International and Affairs at VNIT. His leadership in coordinating GIAN initiative and his contribution in engineering education has been greatly valued by both faculty and students. Joining him as our guest of honor is Dr. Kumar. Dr. Keshri is a local coordinator for GIAN courses at VNIT and an associate professor in Department of Electrical Engineering. Next, we welcome Professor Kailas Wasewar, Head of Department of Chemical Engineering and coordinator of this workshop, whose dedicated efforts have made this event possible. And finally, we welcome Dr. Diwakar Shende, Associate Professor, Chemical Engineering Department, VNIT, coordinator of this workshop and a driving force behind this development of this course. To mark the auspicious beginning of this event, I now invite all the distinguished guests to join us with for the lighting of the lamp, symbolizing the light of knowledge and wisdom that will guide us through the insight of to be shared in this course. Sir. With the ceremonial lighting of the lamp, we mark the commencement of GIAN course on Advances in Engineering Design, Energy Transition and Project Development. This symbolizes, the symbolic gesture signifies the official inauguration of our journey together. Thank you all the honored guests for inaugurating this event with the traditional light lamping. We now extend a floral welcome to honor each of our dignitaries. I kindly request the Honorable Director sir to present a bouquet and memento to our chief guest, Dr. Swatantra Kumar Shrivastava. Wasewar to present the bouquet and memento to Professor Bucheli sir. I request Dr. Shende to present the bouquet and memento to Dr. Kumar sir. Dr. Shende, I would like you to invite for a floral welcome and with memento of Professor Wasewar. Lastly, I take the opportunity to present the bouquet and memento to Dr. Shende. Thank you all for this wonderful gesture of respect and welcome. To provide us with the insight of the GIAN course and its objective, we have with us Dr. Shende, coordinator of this workshop. Dr. Shende has been an exceptional leader in bringing this course together, ensuring it aligns with the latest development in engineering, design and energy transition. Dr. Shende is an elected fellow of Indian Institute of Chemical Engineers, Maharashtra Academy of Science and Institution of Engineers, and in addition to the member of other reputed professional bodies like American Institute of Chemical Engineers and American Chemical Society. Dr. Shende started his career with chemical engineering in Emerald Petrochemicals. Significantly, he joined the teaching profession at Madhav Institute of Technology and Science, Gwalior. He joined the Department of Chemical Engineering, VNIT, Nagpur, and presently working as Associate Professor. Sir, you may speak.
Thank you, Anjali. It's my privilege to brief about the GIAN course. First of all, the respected and honorable Director, Professor P.L. Patel sir, Professor B.M. Buchandi sir, who is holding the charge of Dean International and Alumni Affairs, Dr. Ritesh Kesari sir, who holds the charge of local coordinator GIAN at VNIT. Then our chief guest, Dr. Swatantra Shrivastava, who has travelled all the way from Germany. My HOD, Professor K. Wasewar, who always support such kind of workshops and each and every activities one would like to. Then my faculty colleagues, dear students and participants, a very warm welcome to you all. It's my privilege to tell about the GIAN course. The topic of the GIAN course is Advances in Engineering, Design, Energy Transition and Project Development. you may see that it may not that much catchy in the world of artificial intelligence, machine learning, and so many catchy words which are present day we are looking into. But it is need of the hour, right? If you see the sustainability goal and sustainability requirement in the present era of civilization, the topic is very essential and need of the hour. We will be covering many good topics, and those are related to the hydrogen plant, climate change in CO2, energy transition, energy technologies, then low carbon technology, hydrogen as solution, stoichiometric and engineering calculations which will be involved everywhere, so that also we will be covering. Then heat transfer and integration, piping and control valves, and we will be covering the safety aspects also, the tutorial also, and the concept of neutralization which leads to the project life cycle. So we will be taking benefits of the large and heavy experience of Dr. Swatantra Shrivastava. Around more than 20 years he has worked in this particular area, and I strongly believe that each one who will be going through sincerely through the courses he will be covering, so it will be beneficial. So with this short brief, I request Anjali to proceed further. Thank you.
Thank you, Shende sir, for your enlightening introduction. We are honored to have with us Dr. Keshri, a noted figure in engineering research and energy transition. Dr. Ritesh Keshri received BSc and MTech from National Institute of Technology, Jamshedpur, both in electrical engineering, and PhD in energy engineering from Department of Industrial Energy, University of Padova, Italy. Since August 2015, he is in the Department of Electrical Engineering, VNIT Nagpur, and is at present as an month from European Union. First prize as a student team leader of the University of Padova in Class 3 of Formula Electric and Hybrid. Best paper award of IEEE transaction on industrial electronic, and Visvesvaraya Young Faculty Research Fellowship for 5 years in 2017. His research interests include power electronics and electric drives for electric vehicle propulsion and charging infrastructure. I would now like to invite Dr. Ritesh Kumar Keshri as our guest of honor to share his perspective with us.
Good morning to all, and it is a privilege for me to be a local coordinator of GIAN program, and we started this GIAN program under with the initiation of Professor Shende in 2016, and I was fortunate to host first GIAN program of VNIT, and then after so many GIAN programs have been organized. So far we have organized 22 GIAN programs, in which major GIAN programs were organized from electronics and electrical department, and other departments, almost each of the department has organized this. So this particular GIAN program is an opportunity for us to get interacted with faculty members from the foreign origin and who have excelled in their work. And actually this was an agenda of the government that invite all the foreign faculty members who have done research work in the area which is going to lead the world in very near future. So we have been very successful. So far GIAN phase 1 and 1 to 3, 1, 2 and 3 is completed. Just third is on the verge of completion, and more than 2000 courses have been approved, and approved, and 1800 courses have been already successfully executed, and at present we are in the fourth phase of GIAN program. So I also request Professor Swatantra to please refer your colleagues also, and it will be so great if you can also suggest that what could be the cutting edge technology which is going to come, so that our faculty members can also take the opportunity to get explored with you. And it is not like what I also request, that it is not like that just a talk for you and for 5 days, but it will be also as an opportunity for faculty members of VNIT, so that with you we will have opportunity of collaborative work, and so that in the coming 5 years we can come up with another cutting edge technologies. So with this, thank you a lot, and I welcome Professor Swatantra for this GIAN course.
Now we are honored to have with us Professor Wasewar sir, Head of Department of Chemical Engineering and Coordinator of this workshop. Professor Wasewar's work has been fundamental to advancing sustainable design in chemical engineering. He has inspired both students and colleagues alike. Professor Kailas Wasewar has been in Chemical Engineering Department, VNIT Nagpur since more than 15 years, and he was visiting professor at Kyung-hee University, South Korea. He has more than 25 years of industrial research and teaching experience from various reported organizations such as Indian Institute of Technology, Roorkee, India, and Birla Institute of Technology and Science, Pilani. He was Associate Dean and Education Technology and Library and member of Board of Governance of VNIT Nagpur. For years 2020, 2021 and 2022, with 2023, Dr. Kailas Wasewar has been included in world's top 2% scientists in chemical engineering as per survey done by the Stanford University. Presently, Dr. Wasewar has more than 200 SCI Scopus Index journal publications, more than 100 conference papers, 6 Indian patents, 1 Australian patents, 1 edited book, 5 edited proceedings, and 35 book chapters. He has guided 1 postdoc fellow, 20 PhDs, 18 MTech, and 102 BTech with 7 ongoing PhD students. He has more than 10,000 Google Scholar citation with H index of 16 and I index of 176. Professor Wasewar, please come forward for your lectures.
Very good morning to all of you. Honorable Chief Guest Dr. Swatantra Kumar Shrivastava, Process Manager, here Liquide Global, Germany. Honorable Professor Premlal Patel, Director VNIT Nagpur, Professor Kishore Purchandi, Dean International Affairs, Dr. Ritesh Kesri, GIAN Coordinator, Deans, HOD, faculty members and coordinator of this event, Dr. Shende, students and participants. Welcome to this particular event. On behalf of Department of Chemical Engineering and VNIT Nagpur, I welcome all of you for inaugural function of the 1-week global initiative of academic network course on advances in engineering, design, energy transition and project development, which is during 11 to 15 November, which is organized by Department of Chemical Engineering, VNIT Nagpur, to say about the Department of Chemical Engineering, which was started in 2006 with 8 faculty members which were joined in 2008. Now we have vibrant 70 faculty members with 120 intake of BTech students, 22 of MTech and PhD students. Presently department has total almost 400 students, and department also recently proposed the new UG program as BTech Chemical Technology in Bioprocess Technology. Department has various sophisticated instruments which include UV, GC, HPLC, FTR, BET, rheometer, TGA, PSA, XRF, etc. and also the well-equipped computer lab. Department faculty members are actively involved in research in the field of biomass valorization to the wastewater treatment and biotechnology to nanotechnology, conventional approaches to the innovative and sustainable approaches for societal and environmental benefit. Department has handled more than 25 research projects worth around more than 10 crores sponsored by various agencies like DST, DBT, DRDO, DAE, BRNS and various industries. And proudly say that one of our faculty member also received a grant of almost 11 crore from DST for the Center of Excellence on Waste Management Technology, and I congratulate him for that great achievement, and we proud for as a Department of Chemical Engineering. Department has also the more than 800 research publications in various SCI, Scopus and reputed international highly indexed journals with more than 600 conference papers, book chapters which is around 150, regarding patents, more than 20 granted patents, few are already published patents also in the Department of Chemical Engineering in the credit of. Also there are 25 filed patents. Till now 60 PhD students are completed from our department and presently 25 are ongoing. Also department has more than 30,000 citations if you go for the cumulative one. In 2009 we conducted first workshop on department in Department of Chemical Engineering, and the legacy was started, and almost more than 60 workshop, maybe of the 2 days, 3 days, 5 days and 15 days workshop we have conducted, and mostly sponsored by the SERB, DRDO, GIAN, AICT and few are the self-sponsored workshop. Department also conducted 10 conferences, which is the one of the best for our department, and one regular feature of our department is the chemics, which was started from 2014. Department has also the IICT and AICT chapter. Recently our PhD students also got the many prizes in various events like hackathon and other related competitions. Also our faculty members are actively involved in administrative responsibility and various outreach activities. Our 3 faculty members are listed in world's top 2% scientists and many more achievements of the department. I think this is enough for our department. Once again I welcome all and wish for the best time during the workshop and enjoy green campus of the BNIT. Thank you.
Thank you, Professor Wasewar. Next, we are honored to have with us our guest of honor, Professor Shende. Sir, to introduce Honorable Director, Professor Patel.
It's my great privilege to introduce our Honorable Director, Professor Premlal Patel, who took over as the Director of VNIT Nagpur on 21st May 2024. Professor Patel is currently a professor in Department of Civil Engineering at SVNIT Surat, specializing in hydraulics and water resources. Professor Patel has an extensive academic and administrative background. He served as the Deputy Director of SVNIT from September 17, 2019 to September 16, 2022. In addition, he has held the position of Dean of Postgraduate Studies, Dean of Research and Consultancy, Dean of Academic Affairs, Head of the Civil Engineering Department, and many more administrative positions. Before joining the SVNIT Surat, Professor Premlal Patel was the Associate Professor in Civil Engineering Department at Delhi College of Engineering, now known as the Delhi Technological University, for 8 years. Prior to his academic career, he served as an Assistant Executive Engineer in the Border Road Organization, Ministry of Road Transport and Highway, Government of India, from 1995 to 1999. Professor Premlal Patel has completed his bachelor degree in civil engineering from Government Engineering College, Rewa, Madhya Pradesh. He then pursued his master and doctorate in civil engineering from IIT Roorkee. His research area are diverse and impactful, including river mechanics, flood control, hydraulic modeling, optimization of water system, impact of climate change on water resources. So there are many more activities he is performing, including research, administrative and the other social benefit. With this word, I request Professor Premlal Patel, please address the
Very good morning to all of you. Our guest of today's function, Dr. Swatantra Kumar Shrivastava. He is foreign faculty, process manager, Air Liquide Global and ENC Solution, Germany, GmbH, Frankfurt, Germany. Our Dean International Affairs, Professor Shende, Head of the Department Chemical Engineering, Professor Kailas Wasewar, and he also the coordinator of this particular GIAN program. Dr. Diwakar Shende, who is another coordinator of this particular GIAN program. Dr. Kesari, who is the local coordinator for GIAN program. Faculty friends and all the participants and the students. I would like to welcome you all on this occasion wherein we are in the process of inauguration of very important GIAN program, that is on advances in engineering design, energy transition and project development. So I would like to also welcome you in the VNIT campus, all the participants who are from other institution over here. Basically our VNIT is located in 214 acres land, and it is completely, you see that campus, it is completely green campus. As well as this VNIT is concerned, VNIT ranked 39th rank in engineering category this year, and in engineering category of course, and 10th rank in architecture and planning category. We have basically 5,000 students in the campus. We have 9 undergraduate programs and 23 postgraduate programs are there. Almost all the departments are having these PhD academic programs. Now very recently we have instituted the new position of Dean International Affairs. So a lot of expectations are there that we should reach out to the global level, and such kind of can say GIAN program wherein Dr. Kumar Shrivastava have come up. Such kind of programs are very much desirable to develop the international link with our faculty and students and develop some collaboration, maybe in terms of joint research projects, maybe joint publications, so that in future we can have more link to the other institution. I could see Dr. Kumar Shrivastava is basically the PhD graduate from TU Dahat, if I am not wrong, and then he is continuously working in the industry, and he has a lot of exposure in the area. So I am sure that his presence in the department will have more collaboration with faculty and the students. I am sure the participants who have come from all over the country, they will meet our this faculty who is here, and you will develop your relationships in terms of academic relationship for your future endeavors. As far as the Department of Chemical Engineering is concerned, it is an upcoming department, and I could see that a lot of contribution is generated by our head of department, Professor Wasewar, and it is a very upcoming department. You can see 3 faculty who are there in top 2% at international level. The list which was prepared by your Stanford University. So I am sure that you can see that kind of, you can say, output is there from this department. Lot of projects, patents, and I could see lot of development taking place in the agricultural base. I could see Professor Sachin doing a lot of work in that area. So I am sure that this department is very upcoming, and by presence of such kind of faculty, like Dr. Swatantra will develop more intense collaborations, and I am sure that we will have good projects and publication in time to come. So I would like to convey my best wishes to all the participants, particularly who are here, to have the very nice time. I think it is for I think 7 days program. It is 7 days? 5 days program. So I think 5 days is quite good time, 11 to 15, okay. So I think that period will be utilized and have a good academic environment during the program. So thanks for inviting me to be part of this event. Thank you very much. Thank you.
with us our guest of honor, Professor Shende.
Now director is not there, we are all friends. Formally introduce.
So, dear friends, I must first thank the course coordinators for inviting me here. And as already said, I happen to be the first GAN coordinator of this institute.
And initially when this came, people were scared of it because people had heard about so-called FDPs, faculty development programs. And let me tell you, in Indian academics, especially in engineering, FDPs, they do not have a very positive reputation, because in history many people, they have done it just for the sake of you people are, I mean, very young people, but before 25-30 years the FDPs were done for the sake of getting some internal promotions and all those things. So there was no concept of I mean, FDPs will offer you advanced knowledge, this, that, something like that. And then when when the GAN program came, it came with additional terminologies like global initiatives, then networking. So these terminologies to Indian academics, they were little bit new. So obviously people were under pressure, and once in around 2016, I was called that time by director. That time director was Professor N.S. Chaudhary. One day he called the letter and you read and prepare for it. I told him, sir, I am already in charge of 6 activities, so 7th won't make much difference. So I am requesting you to take care of this activity also. And as you already know, request from a director is more or less an order. So that is how I got this responsibility. And then people were not much enthusiastic due to that level of similarity to FDP. So I had to move that time department to department, requesting people to apply under this program. Because after all my efforts, when I was sitting in my department and sending emails, I could get only around 19 to 20 proposals, and I was sure that at national level, if you are submitting 20, then you will get only 2. So I had to go department to department and convincing people that this is a different activity, it is not FDP, and moreover, the coordinators are going to get national level name, fame, and so on. They will get your own departmental faculty members, PhD students. They are going to get the opportunity to interact with international faculty, because let me tell you, though we have been NITs, the opportunities, sir, before 2014 to interact with international community were comparatively less. Most of the times the probability was that some Indian faculty member, those who are in foreign countries like you people, we used to invite and used to have interaction with you people. But this GAN opportunity, GAN courses, they have given us opportunity to invite people, and first time might be in history for NITs that financial provision is also made for the same. As far as academic part is concerned, of course, our students, our teachers, I mean the invited guests, many times in smaller institutes like state government institutes or might be in private institutes, teachers, students, they may not get opportunity to directly interact with foreign faculty, but this activity has made this opportunity available to all. Now when we are talking about this, only earning knowledge is not the intention. As I have already said, global initiatives. So we are supposed to form networking at global level. And as far as our teachers are concerned or PhD students are concerned, many of the PhD students, they might be handling their undergraduate practicals. So this opportunity will enrich their knowledge. And as far as teachers are concerned, if you are coming from different institutes and you are specially handling undergraduate and postgraduate students, what is expected is whatever knowledge you earn, whatever contacts you earn, the knowledge which you have earned through this activity, it is expected to disseminate up to the lowest possible level. Then only the aim of this particular activity, I mean UG and UG students and PG students also, then only the true motive of this particular program, which was framed by Government of India, will be successful. As far as this activity is concerned, today's program is concerned, again I will like to congratulate the coordinators, because let me tell you, we have been fortunate. As I told you, earlier we got only 20 proposals, then after our efforts it shot up to 90. We submitted 90 proposals, out of which 70 were in the first phase and 20 were in the second and third phase. So out of these 60 proposals approximately, 22 were awarded to VNIT. And let me tell you, our strike ratio means ratio awarded divided by the total proposal submitted. It was second in India. Only one IIT was above us, and we were the second. And I am very happy that after I relinquished this responsibility to Professor Kesari, he is also trying his best. You also may have to make trips to IIT Hyderabad. That time it was IIT Kharagpur, so a few times I had to visit there for forwarding our proposals and all that. And fortunately, Professor Kesari is also a very dynamic personality. He keeps on moving on here and there. Don't go on his personality. His the coefficient of dynamics is very high. So I am sure that in his duration and tenure as a coordinator of GAN activity, VNIT GAN activity will see newer higher-ups, and all of you will enjoy, those who are especially coming from outside the stay in Nagpur. I am sure that Department of Chemical Engineering and the organizers, they will take care of you. If you are happy with the arrangements, tell the world. If there is some lacuna on our side, please let us know. We will try to improve ourselves, and next time we will try to offer better facilities to all the participants. And these days Nagpur climate especially is very nice. I will say Nagpur is at its peak. Otherwise in summer it is red hot, and rainy season is also quite nice here. But November, December, January, they are, we call it pink months of Nagpur. You may get many oranges, those who are coming from outside. So please enjoy your stay on campus. Please enjoy your stay in Nagpur city, and I hope after going back you contribute to your institutions in whatever way possible, because that is the motive of this kind of activities. As I have already told you, organizing the FDP is not, okay, but you should get global exposure. Your undergraduate and postgraduate students also should get global exposure. That is the intention of this program. And as far as Professor Swatantra Kumar is concerned, sir, I will again request you, already requested by Honorable Director, but as Dean of International and Alumni Affairs, I will like to request you to take this interaction, collaboration, networking further, and please suggest us your other friends, those who can submit GAN proposals. I am not only talking about chemical engineering department. You may have your friends across the disciplines there in your university, in your institute. So you may please suggest their names also. We will encourage our teachers to submit more and more GAN proposals, and I think that way we will strengthen the interaction between your university and our institute. So that's all from my side. Thank you. Thanks one and all.
Thank you, sir, for your encouraging address. We are deeply honored to have our chief guest, Dr. Swatantra Kumar Shrivastava, a visionary in the field of engineering with us today. Dr. Swatantra Kumar Shrivastava holds a master degree from IIT Kanpur and doctorate from Technical University of Delft, Netherlands. He has worked as a process engineer for last 20 years in leading engineering houses and licensors across the world. He has worked in different roles and in different phases of projects such as proposal, basic and detail engineering, commissioning and startup of the plant. He is known expert in designing hydrogen manufacturing unit. Trainer has 5 granted and 3 published and over 10 submitted worldwide patent in the area of hydrogen technology since 2012. He has been working with Air Liquide ENC Germany within the hydrogen business unit of the group. He has covered the whole project life cycle, beginning from conceptualizing, feasibility study, technical proposal, management, etc. It is now my honor to invite him on the stage to share his valuable insights. So,
but still, good wishes from my side to you and your family. I will not spend time on myself because, as I said, you already provided detailed introduction. You know, in Ujjain, now and then I hear from people, it's getting hot in year by year. So I'm pretty sure everybody in the room already heard about climate change and those kind of things. And the CO2 the main responsibility of the greenhouse gases, of which CO2 is one of them. And the rapid industrialization we had over the last 2 centuries led to huge amount of CO2 release. So don't worry, I will not have my slides finished here now, but just to bring the perspective. And the hydrogen role in the future energy perspective. So those are the topics I will be covering. As you already know, my 20 years of professional experience was in industry. So small correction, I was never a faculty, I'm not a faculty. I was always creating value for our shareholders. I was always in the industry, professionally working there. So that's why I'll also touch upon the advances in engineering design and how nowadays energy transition business is moving from traditional coal, oil and those kind of fuels to renewable power and as I said, the hydrogen perspective. So those are the topics I will be covering. I mean, I was 20 years working outside, so I was disconnected with such functions, absolutely fascinating, absolutely humbled, and honestly I never shared knives with such reputed people, so absolutely honored and very happy to be here. I was already here last year for one hour session Dr. Shende arranged. So beautiful city, beautiful campus, and I already see people excited, so I hope I will meet the expectation. So from my side, once again, welcome you all, and yeah, that's it. So I do not have a long speech, I don't want to bore you with this. Once again, welcome to the course, and as I said, I'll try to meet the expectation, and yeah, thank you very much.
thank you, Dr. Shrivastava. To conclude today's inaugural function, I now call upon stage Ms. Shrawani Pathak to deliver the vote of thanks and formally close the inaugural ceremony.
Good morning to all respected dignitaries, esteemed guests and dear participants. It is my honor to deliver the vote of thanks on behalf of my coordination team on this special occasion marking the inauguration of the GIAN course on Advances in Engineering Design, Energy Transition and Project Development. First, I would like to express my deepest gratitude to our chief guest, Dr. Swatantra Kumar Shrivastava, for gracing this event and his esteemed presence. My sincere thanks to our guest of honor, Professor K.M. Bhushandi sir, for his encouraging words and for lending his support to this initiative. I would like to thank Dr. Ritesh Kumar Keshri sir, the guest of honor and local GIAN coordinator at VNIT, for his valuable guidance and support in organizing this course. I would like to thank Professor Premlal Patel, the Honorable Director of VNIT and patron of this course, for his vision and leadership. A special thanks to Professor Kailas Wasewar sir, the head of Department of Chemical Engineering and coordinator of this workshop, for being with us and supporting the event in all possible ways. A special thanks to Dr. Diwakar Shende sir, the coordinator of this workshop. A big thank you to all the participants for joining us. Your enthusiasm and eagerness to learn are what make this course possible. I would like to thank all our invited speakers who will be sharing their expertise with us over the next few days. Thank you to all our esteemed guests for being with us today and for setting the stage for a fruitful and inspiring course ahead. With that, we conclude the inaugural function and move forward with our sessions. Wishing everyone an insightful and rewarding experience in the days to come. Thank you all, and I request all to enjoy the high tea.
One little announcement. In my tenure for the 22 GIAN courses, the total students count was 960. So now I came to know that it is 32. So it will now become 992 total participants participating in this GIAN program. So I hope the chemical engineering department gets that opportunity to strike 1000. You people have submitted, when I was, before a few months only I handed over the charge to Professor Kesari. So I know from your department 3-4 courses have already been submitted, and I am sure that this department will get the opportunity to strike 1000 GIAN participants for VNIT. That's all. Thank you.
So we already come to safety at design. So this wall was designed in a way that there could be a possibility that somebody can remove the actuator and the flange which is holding the pressure inside the vessel. So safety doesn't start at the plant or at the operation, but it already starts at the design level.
All of these previous incidents resulted in fatalities or serious injuries. CFD believes that the recurrence of these types of incidents point to the need to redesign plug valves so that it is very difficult to accidentally remove pressure-retaining components.
The best way to address this type of incident would be by prevention through design of new plug valves. But in the meantime, facilities should clearly label pressure-retaining components on existing plug valves. For example, through color-coded paint and warning signs so that workers can identify them more easily.
As a result, the CSB made recommendations to the American Society of Mechanical Engineers and the American Petroleum Institute to revise their plug valve design standards to require facilities to clearly mark all existing plug valve pressure retaining components and require that new plug valves be designed to prevent the inadvertent removal of pressure retaining components. The second safety issue found by the CSB is providing workers with conditions, procedures, and training to safely conduct work. The CSB found that LyondellBasell did not thoroughly assess the risks of the actuator removal work to assure that sufficient procedures and safeguards were in place to prevent exposure to process fluid.
At some facilities, a risk assessment may determine that depressurizing and de-inventorying equipment is required before removing plug valve actuating equipment.
The CSB also found that LyondellBasell failed to provide the turn-to crew with a written procedure and allowed the work to be done without LyondellBasell's oversight because of the perceived simplicity of the actuator removal. Furthermore, the CSB determined that neither LyondellBasell nor Turn2 trained the work crew on the steps necessary to safely remove the actuator.
And LyondellBasell performed a risk assessment to ensure safeguards were in place during actuator removal, as well as provided the Turn2 work crew with written procedures, proper training, and oversight. This incident could have been prevented.
As a result, the CSB recommended that LyondellBasell update company policy documents to require that procedures are developed for properly removing actuating equipment from plug valves, and to require verification that contractors are competent, adequately trained, and qualified to perform work.
As this tragic incident has shown us, even a simple task can turn deadly if it is not properly performed. It's time to improve the design of plug valves and take other protective actions, such as ensuring that clear markings are visible on all existing plug valve pressure retaining components, and workers are properly trained before conducting maintenance. Vital steps like these can go a long way in injury prevention and help save lives. Thank you for watching this CSB safety video.
For more information, please visit CSB.
So we pretty much saw that this is a reactive approach. Now they start designing plug valves in a way that it's not possible to remove this plant. They also worked on their procedures and training. So, any views from your side? Any key point and quick comment? Just wanted to make it more interactive. Like the video or is this only? Okay, maybe it will take few hours. But we have 5-month program. So first day I help everyone. And for next 4 days I would like to have 4 volunteers to bring up a case study. We just spend 5 minutes and 1 slide or 2 slides. Just take up an past incident. Who is going to raise hand? No one? And then I will ask, request Dr. Shende to assign power of. Okay, now think about it. Very good. Thank you. We have 1 volunteer. Thank you very much, Dr. Kalpana. Okay, think over it. Otherwise, Dr. Shende will forcefully assign someone. Yeah, the key points I already wrote down here. We saw from the video. So it's mainly about the contractors for irregular maintenance. So safety starts at top of the management. There must be a culture. People or employees should not be discouraged to talk about safety. Many times it happens that you see some unsafe behavior or activity, but you are scared to talk about it. And that's management responsibility to encourage or to bring up a culture where you are free and not scared of to talk about anything unsafe or so on. So it's about the culture. So it starts at the management level, but it's not only the responsibility of management. It's the responsibility of everyone. So everybody has to contribute to perform all the activities safely. So there were probably you have already seen it from your some courses also. Accident actually happens when, or they happen not because of one mistake. They normally happens because of series of mistakes. So there is a nice figure with the block with several holes, several layers of protection. But when all these layers falling apart, then we have such accidents also. So in this case, there were several things happening. There was no training, emergency response was delayed, and probably you saw from the video also. It's a very congested area, and the way the acetic acid was coming out, probably somebody would be pushed down to the and it was on the higher level. I would have loved to do that before any other let's say business. So safety is the first one. That's also at my heart. One of the most important invention of last century was Haber-Bosch process for production of ammonia. Why is that? Here you could see how the population, the global population increased in the last century. And if we wouldn't have the Haber-Bosch process invented, we would have only, that's the curve we would have followed for the food production. So normally, the biomass is made up of 4 components: carbon, hydrogen, oxygen, and nitrogen. Whenever we are growing crops and using them, so we are taking carbon, hydrogen, oxygen, and nitrogen from here. Whatever we take from earth or soil, we can fix it back, or naturally it is fixed back, the carbon, hydrogen, oxygen by photosynthesis. Right? But there is no other way to fix nitrogen back. And the Haber-Bosch process was about the ammonia production, and ammonia production leads to production of several fertilizers. And in this way, nitrogen from atmosphere was fixed back to the soil, which cannot be done by photosynthesis for carbon, hydrogen, and oxygen. So that's one of the most important, let's say, invention of the last century. So you all must be proud of being chemical engineers. So nowadays it's only IT and software who are contributing, but don't forget, we also had our share of contribution to the society. But unfortunately, the same very good invention led to, probably you have seen this slide last time. Yeah, the same invention also led to production of explosives. The same ammonia can be used, so that's not good for the society. So some people say it was a very good invention, but because of this, also we have a lot of fighting going on in the world. Let's continue on the safety. It's a small flow sheet of ammonia, Haber-Bosch ammonia process. So normally, what's the pointer? Right. So normally Haber-Bosch process starts with the natural gas, which is predominantly ammonia, methane. And normally you refine this methane to, we'll see this in next sections. So natural gas to CO and hydrogen, and further this hydrogen is converted to ammonia using nitrogen from the air. So here you could see the operating conditions. Here we're talking about somewhere around 700 degree, 800 degree. The operating pressure is somewhere around 80 bar, 90 bar. We are talking about here hydrogen, highly flammable. We are talking about natural gas, once again highly flammable, operating at very high pressure. So, looking at this flow sheet and looking at the operating conditions, so what are the process hazards or risks you can think about within this plant? I think I already gave some hints. Pressure? Yeah, you cannot control the pressure, and something can explode that can lead to flying of heavy metal. That's one thing. Yes. Methane gas, and what is the hazard associated with methane? What's the major hazard associated with methane? What's the risk? Flammable? Yes. Yes. Fire? So fire is a hazard. Yeah. Storage of methane? Yes. If you have loss of containment of stored methane, you can have fire. Do you know about the fire triangle? The three things? Yes? Yes? Can you explain?
It is a fire starts from the heat source, the oxygen that drives the fire,
Oxygen, yes.
and the ignition.
And the ignition. So there are three things for fire, three important things. You need to have all three of those things. Something flammable, oxygen, and a source of ignition. Any other hazard you could think about. So I wrote few of them here: high temperature, high pressure. Some of the things which probably we forget. It's a plant, heavy traffic. You have big trucks moving around here and there. It's also corrosive solution, falling from heights. We're talking about these columns which are 50 meter, 60 meter high. We just saw one of our friends was standing on the sofa. So normally anything above 1.8 meter, you're not allowed to just stand like this. You need to harness and you have to hang it somewhere. Because we don't realize it, but please don't try it. But if you fall from 1.8 meter, above 1.8 meter, serious business. So falling from heights, oxygen depleted environment. Imagine you have some maintenance in one of these columns. It's very congested, very less oxygen, and in the past, many times it happened. I've not seen it myself, but within our plants, people going down, and they just get unconscious. So as I said, we are working with high temperature there, so you could imagine there must be a lot of refractory, a lot of insulation. Some of these insulation materials are also carcinogenic in air. Yeah, they stick to your lungs and can lead to lung cancer and that thing. So those are some hazards or risks, I think. Okay, I think we can skip this slide because we already have a lot of introduction in the first 1 hour. But once again, to repeat from myself, I think probably already noticed I'm a safety enthusiast. Talking in these 5 days a lot about safety. And this one saying, it's never too much to talk about safety. It's never too much. So by training, I'm a chemical engineer, like most of you in the room, and I always worked in the industrial research, never associated with the academic research, and started with conceptual design. I've also experienced with the starting of the plants and other site activities, but I never operated the plants. I started them, but I never operated the plants. Okay, let's take 5 minutes. I think it's a big group. I would have. Yeah, so from objective from my side. So in the next 5 days, I'll try to give you clear of industrial process engineering, how we design the plants, what are the advanced tools we are using. And I'll give you also a little bit about the various project phases. You do the conceptual process design, then you move to basic engineering, detail engineering, and you start erecting the plant, and you start the plants projects phases. And I will try to establish a link between what we all learn during our undergraduate courses and how those, let's say, course knowledge is applied in the real world. On the course content, we'll be talking a lot about GHG emission, CO2, and Mr. Kalpana will be helping me maybe on the later stage. So we are moving from carbon-intensive source of energy to low carbon or even to no carbon, carbon-free energy sources. So how this energy transition is facing in the last 10 years or so, what are the future perspectives? Coming decade or coming 30-40 years. And also one of the most important objectives for this course for me is everybody is back to the loved ones safely. There's no incident here during these 5 days. Not only here but also during the non-course hours.
So I joined the industry. The name of the industry was Clean Hydrogen Technologies India Private Limited. It's in the Nashik. Okay, I joined the industry in January as an intern, 3 months internship period. Then they offered me offer letter to join the industry. So after few months, the project was ongoing. The project was on the hydrogen production from the methane gas. So it was basically torture and hydrogen.
Turkey's hydrogen.
Yeah, torture.
Pyrolysis.
Yeah, pyrolysis, methane pyrolysis at 950 degrees Celsius. Then when the reaction was carrying out, the reaction was basically the endothermic reaction, the pyrolysis. So the reactor was made of HK40 material. The material of the reactor was HK40. And the heating material, that heating source was the induction source. So there was a little mistake in the coil length, the induction coil length, the copper length. There was a little mistake. What happened? At single point, the heat concentration was so more. At the concentration, heat concentration was more, the temperature rise above 950 degrees Celsius. We have the thermocouples and everything plugged into the reactor. But the problem was where the heat source was major, there was no thermocouple to guide the temperature or to shut down the induction machine. So what happened? The temperature was rising. The pressure inside the bar reactor was 10 bar, and the flow rate from the MFC, mass flow rate, it was around 110 lpm of the methane liters per minute. So what happened? That the reactor got leaked. And and there was a catalyst inside, metal catalyst. That was to enhance the reaction. Okay. So what happened? The material started to come out from the hood before the gas. That was the point which stops the gas from directly leaking out. And there was an insulation layer on the reactor. So after some time, the material from the reactor totally get outside the reactor, but it wasn't noticed until due to the insulation layer, neither the thermocouple detected. So after some time, like 2 to 5 minutes, the gas came out directly, and there was a flame from the reactor. So we had to immediately shut down the induction fire and the generators and everything, and start rushing to extinguish the fire. The first point was to remove the pressure from the reactor. So the plug flow valve or pressure control valve was released totally. The hydrogen was vented to the atmosphere, and then suddenly the reactor was stopped. This happened 2 times in the reactor. Yeah, I was there. My shift just started at 2 p.m. and I recently get there and just handovering all the things from my colleagues.
The major topics will be covering is climate change, greenhouse gases. What are the greenhouse gases we have? Climate change, as I was saying, the introductory speech or talk, GIAN, almost everybody now and then say it's getting every year hot and hot, hotter and hotter. Always that's the case in Nagpur as well. So not here, probably effect is not so much here, but in European countries it's drastic. Being 20 years there already, I never experienced temperatures like 32, 33, but nowadays for last 5 years, 33, 34 degrees is absolutely common. So we all are seeing the effect of this climate change. So we'll see what are the responsible, let's say, gases, and how we are moving from energy intensive or carbon intensive fuels or energy sources to low or zero carbon energy sources. How this energy transition is happening. Since I spent almost 15, 16 years in industry doing projects, so I'll be sharing my experience on how we design industrial plant. We'll be using hydrogen as a hydrogen manufacturing process as an example. And moving from carbon intensive energy source to low carbon, or let's say zero carbon, renewable power is going to play a major role, mainly the solar, PV and wind, but hydrogen also has its parts. We'll see where exactly hydrogen fit into the equation. So I think these things we can skip because they all have the detailed agenda. So any questions so far? Please.
So yeah, as we have seen, safety. Yeah, regarding safety, accidents in industry cannot be avoided. There is industry, there will be accident, but it can be minimized. How? From learning your past experiences. From learning through your past experiences. CSB, which is from US, community, but in India, we don't have any such organization which will report the accidents, investigations, right? Why this is happening? What is the cause of that accident? How many people died? What is the root cause? Everything was mentioned in the CSB report, right? India is lacking that way. Another thing, right? So, keeping this into mind, what mistakes they did. If we have same plant, we should not repeat the same mistake in our plant. First thing. Second thing. In the there is a green project and there is a brownfield project and the greenfield project. Have you ever heard about this? No. Greenfield project is something which is not yet built, but it is in the conceptual stage. Right? And brownfield project is something which is already established and you want to expand some of its unit, some of its production, or expansion. That is the brownfield project. Now, as a Gaxcon also, all been recommended as in conceptual phase itself, you need to perform the consequences analysis and QRA, quantitative risk analysis. Why? There is a 3D tool, CFD, right? Generally, in India, what Indian people does to get the, your industrial, any project or industry has to be from MOEFCC, right, to be accepted. They do it not voluntary, but as a compulsory. That government has told you and you have to do it, that's all. But in European country or other countries, what happens? They do it by themselves. So the culture, safety culture has to be established. The mindset should be like that. How it will be? Should start from generation of your age. Mindset should change, right? Now, what is the consequences analysis? If I would say that if you had noticed in the previous case also, if any flammable gas, like ammonia is also, if the gas is flammable as well as toxic, so which analysis will you give preference to? Whether to the consequences analysis of flammable gas or the toxic gas? Which analysis will you give the preference to? The same gas could be flammable as well as could be toxic. Which consequences analysis will you give preference to? Which analysis? Toxic. Example, a very good example, well-known example. Bhopal gas tragedy. Yeah, if there is a flammable consequence and if flammable gas, and there is a congestion, defines the congestion, the explosion, level of explosion is defined by the level of congestion, right? How much level of congestion is there? All three-dimensional modeling is there and we do the analysis and everything, right? So there will be explosion, there will be flyaway and something like that. But in toxic dispersion, like Bhopal gas tragedy, innocent people will die because of the industry mistake. Gas may travel anywhere. It can move anywhere, right? It can move anywhere around Bhopal city, along the direction of the wind. People which are inhaling, innocent people all die. It was the worst ever tragedy happened. That onwards many changes has happened. Safety comes into picture, right? So that was all about this. Yeah, there are much spectrum of safety, like process safety management, PSM is there. One is LOPA, layer of protection. Yeah, LOPA analysis is there. So if this thing goes wrong, level indicator goes wrong, then that thing goes wrong, this layer of protection is there. If this failure happens, then that. Right? Then there is a hazard study, hazard analysis. Yeah? So we do the department wise, each and every, all from department, each and every person, from engineering, from instrumentation, from procedure, plant wise. Yeah? All people are gathered, so together, and we divide into nodes of a plant. And then we analyze, if this happens, what will go wrong, Then we define the LOC scenario, loss of containment scenarios. Out of these scenarios, we take them, major scenarios, into picture. In the design phase, conceptual phase itself, you can do this. Major scenarios has been taken from that, and then we bring it into the QRA report consequently. There is a lot of metrics and everything is there. So another subject, 2 to 3 days of subject, right? Anyway, then what is there? If you are out of this LOC, loss of containment scenario, limited scenario, CFD scenario, because it takes days to happen. What you will consider if this particular gas will leak due to any what could be the reason? What could be the reason of leakage of the gases? What could be the reason possible? Come on. Human error. Yeah, but what?
Failure of valves.
Failure of walls is the major, and leakage, corrosion, pipe corrosion, yeah, pipe corrosion, leakage from the walls. Yeah, you must have seen even the Bhopal gas leakage of the walls. There is a safety walls, safety slips. Now, scrubbers not operating well, and hazards. There are the standards that how much hazard you can, combine, or you can have in your industries. All rules has to be taken care. Okay, then LOC scenario has to be taken, and then what is the consequences analysis then? That what will be the consequence if this particular leak happens due to any, and reason, how far it can go, then how will you decide? Then there is a factor, like there are many factors, means that particular concentration will die the people. Chlorine gas of 10 ppm. Yeah? It is hazardous. Yeah? Hazardous to life, there is a word. Yeah? So if this particular ppm, so we will analyze for that particular ppm, different ppm level. What will be the distance? Taking different wind direction into account. We take a combination of all these things. Wind directions, wind classes, Pascal classes, everything, right? Okay. Then that is the consequences analysis of the toxic or the flammable gas. How far? Now, as one of you told that for fire to occur, the fire triangle should be completed, right? So there is a source of ignition. What could be the source of ignition? What could be the source of ignition?
Spark.
Which spark? Electric spark. Other static charge. Other, yeah, in explosive industries, even you have to be discharged, Yeah, and other vibrations. Yes, other. In flammable, if
Somebody
gas
said
leaks.
friction? Somebody said friction? Huh? There is a
Yes, sir.
major source of spark. Huh? So you have very high velocity liquids flowing, and they can also generate big spark. So static charge and very good. Please, sorry, continue.
No, please. Thank you. There could be your motorbike, motorcycle, car, yeah, around people, yeah. There is an individual risk. There is a societal risk. Society. It's a lot big picture, right?
Okay. Thank you very much. Thank you very much. Thank you. Now, as I said, we'll have two sessions or two exercises, and one is actually completely dedicated on HAZOP. So, I'll be giving out an example, and everybody will be doing a HAZOP at least for the two keywords, maybe temperature, flow, high, low.
There are keywords.
Yeah, keywords and guide words. So, we will have one exercise, 1.5 hour fully dedicated for HAZOP and cell analysis, low power and all those things. So you will see. But thank you once again to touch upon those things. So let's start with some dirty stuff. We all say industrialization had many side effects, and nowadays it's not so nice and this and that. But there are many positives of industrialization. So here you could see, I just mentioned one here, the life expectancy went from 30 years, 1850 to almost 65, 70 years nowadays. I think in your generation you cannot think about its reality. People were dying at 30 or 35. So advances in medical field and other fields has led to let's say increase in the life expectancy everywhere, almost everywhere. You could notice a small dip here. This is not working. But you could notice a small dip here. And this one is COVID. So this graph was increasing, and probably this one was the, another epidemic. But that's the one because of the COVID. A real, visible dip. As I said, thanks to the advancement in medical field, there's no big epidemic over the last 30-40 years. Keep aside the COVID we're talking about. When I was studying like you guys in undergraduate, in the psychometry course, I still remember I always do calculations, 79% nitrogen, 21% oxygen, but sometimes you also have CO2 to take into account. And I always had in my mind 300, 350, so 0.03 mole fraction, mole percent, sorry. That's the concentration of CO2 in air. And then I started working in projects, never had to do these calculations, using softwares and everything. And suddenly 3-4 years ago, I was doing some calculation and I found some mistake. And went on the internet and I was shocked to see that now the concentration is not 360, it's almost 420. So just to mention, you miss this 15 years and suddenly see the concentration has fallen from 360 to 420. So thanks to internet I realized why the calculations were not correct. Then I did a small calculation, a small that you guys can also do. That's the diameter of Earth. And I just did a small calculation. We have the atmosphere up to 10 kilometers, about so thin that you can ignore. And going from 360 to 420, if I calculate back to a simple mathematics, the volume of the sphere with the diameter of Earth plus the height of the atmosphere, I ended up with 612 billion tons of CO2 we have released, human society has released over the last 25-30 years. And coincidentally, my calculation were very close to the number I found on the 617 billion tons of CO2 we have released. So, I mean, it depends also on the source of the interpretation found, but more or less this is the range. Almost 600 billion tons of CO2 human society has released over the last 25-30 years. If you want to have feeling of the number, I don't know if somebody has visited a quarry or a cement plant. I cannot put up a picture, but recently I was in a quarry where you mine the limestone. So most of the time cement plant is just beside the source of the limestone. And I saw it was 300 meter by 200 meter and 90 meter deep. So it's a huge hole, almost 10 football field or even more, and can be fitted as for the area, and 90 meter deep. And if you know limestone is CaCO3, and limestone is CaCO3. And you also know the molecular weight of CaCO3? 100 kg per kilomole. And out of this 100, how much is CO2? 40? 44. So, somebody told me that whatever you see here is big for 300 meter by 100 meter or 90 meter. Half of this is released to atmosphere. That already shows you, and that was in solid state, now it's in gaseous system. You could imagine the scale of how much CO2 we have. But what's the problem with the CO2? So here you could see the CO2 concentration increasing, at the same time the pH of the ocean, all the oceans are decreasing, so it's getting acidic. Ocean water is getting more and more acidic. Because if you have more CO2 in the atmosphere, you will have more CO2 in the water or the oceans. So once again, what's the problem with the CO2? It will increase, more CO2. But what has happened is because of the CO2 release, the global temperature is rising. And here you could see how this is increasing over the years, in the last 1 or 2 century, and this graph is actually in parallel to the industrialization what we had over the last 200 years. So there are 2 group of school of thoughts. There are 2, let's say, group of people. One is directly blaming CO2 for this temperature increase. There is also another group of people or experts out there saying that it's a natural cause. So if we see, I do not have this plot here, but if we go prehistoric age, maybe 10,000 years, 20,000 years, there is a temperature increase, that decrease. Some people are saying, let's not worry about that CO2 is responsible for this temperature increase. This is a natural cause. Some religion says famine or some other word. So this is a natural cycle. It will go up, temperature will go up. But for now, for this scope of this course, let's assume or let's agree to this global consensus that this temperature rise is direct result of CO2 human society has released over the last 200 years. So consequences, so what's happening with this temperature rise? As I said, we are experiencing extreme weathers, severe storms, rising sea levels, ocean pH I already mentioned, those are things. Severe health issues, food insecurity, because food production is going down because of this temperature rise. A lot of economic damage, and because of this, the most vulnerable in the society are elderly and young people, and also the unprivileged. Now, how this CO2 concentration increase and temperature rise is correlated. So a little bit of, let's say, technical part is a term called greenhouse effect. Does somebody know about this? Somebody explain? It's on the slide, but I want you also to come up with some technique. So, probably you see already here on the slide. That's the solar radiation what we get. This is something what Earth absorbs. And these greenhouse gases, CO2 is one of these gases. They do not allow the re-radiation of this heat coming from sun back to the upper atmosphere. And that's the problem. If these greenhouse gases keep this heat here in the atmosphere, the lower atmosphere, the global temperature will rise. So that's basically the greenhouse effect we have. As I said, heat accumulation. So heat is coming. So first law, with the balance, what heat comes in, goes out, you have your equilibrium state. But as long as you are disturbing this in and out balance, you will have accumulation. Now, as I said, the CO2 is one of those greenhouse gases. Others are methane, N2O. I don't know if you have heard about N2O also. Not here. So basically N2O is not as such released from combustion. So if you are burning something using air, and burning or combustion means you could have temperature 1800, 1900 degrees. If you are burning methane, here you can have a temperature of 1900 degrees. At 2000 degrees, the nitrogen in air will also react with oxygen to produce nitrogen. It will not stay as inert. So normally we always learn in our undergraduate course nitrogen is an inert gas. So what comes in goes out. But in reality, a very small fraction of nitrogen also reacts with oxygen and generates these NOx. At the flame or the combustion, during the combustion, the NOx which is generated is NO and NO2. It's not N2O. you have combustion at low temperature, you can also have CCO. But once these NO and NO2 are released in the atmosphere, they disperse and then in presence of particulate matters, they convert from NO to NO. So NO and NO, so probably you have heard that NOx is also a big trouble nowadays. Diesel engines, I don't know if you are aware, they inject ammonia or urea to reduce NOx. So NOx in itself is not an issue, but this NOx released to atmosphere and converting to N2O, that's an issue. Now, as I said, there are many gases, but they all are not so, should I say, culprit, bad. So GWP, that's the global warming potential. That's a way to quantify their effect, the greenhouse effect. Right? And this is always reported based on CO2 as reference. So the global warming potential for CO2 is 1, and for other gases, as the number is higher, so GWP is higher, effect is higher, lower number shows the effect is lower. So I don't know if you know methane, very innocent gas, but that's 23 times more global warming potential compared to CO2. So if we are releasing 1 mole of CO2, so if we are releasing, or let's say if we are releasing 1 mole of methane, and we are releasing, it's equivalent to release of 23 moles of CO2. But fortunately, the amount of CO2 release is much higher than the amount of CH4 which is released. Normally we don't intentionally release CH4, but whenever you do natural gas exploration, it's a lot of leakage. CH4 is due to leakage. And I was astonished to know, I didn't know earlier, I was astonished to know that over the pipelines, almost 3% of gas for to transport is lost because of the leakage. So, although everybody talks about CO2, but as long as the society is dependent on natural gas or methane, methane greenhouse problem is also a severe one. It's not addressed so much, but it's also a severe one. We saw 620 billion tons of CO2 over the last 25 years, something like 30 billion tons every year. Compared to CO2 and N2O, what NOx would be not even million tons, factor 10 to the power 4. But the global warming potential of N2O is 296, almost 300. It's 300 times more, let's say, severe than CO2 is. Then we have some hydrofluorocarbons. I don't know, I think in India also they are banned. Most of those are already banned. 40 years ago they were considered very good components because of their insulating properties. A lot of those things were used in refrigeration, insulation, etc. But in Western countries almost banned. In India also, as far as I remember, most of those are already banned. So here we come to the first calculation. So here you could see I'm presenting here two composition of coal. It's almost 35% carbon. I remember it was an ultimate analysis, approximate analysis. So that's the ultimate analysis of the coal. It's almost 35%. Let's take an example of the second one. It's 34% coal. And if you remember from your stoichiometric classes, calculate back how much CO2 is released from 1 kg of coal and how much heat will be released from 1 kg of coal. And probably you could see 0.36 here. Can somebody tell what this 0.36 should be or could be? So we started with the basic 1 kg of coal. Sorry?
Efficiency.
Very good. Thank you. Efficiency. Efficiency of energy to power. So that's a typical efficiency of a coal-based power plant. It can be 1 or 2% here and there, but let's take for the simplicity purposes. So we started with 1 kg of coal. It's almost 345 gram of carbon, 44 and 12. I don't need to say. Molecular weight of CO2 and the mole weight of elemental carbon. And the last row shows the calorific value or the heating value of this coal. It's almost 3,300 kilocalorie per kg. That gives us 4.2 conversion of calorie to joule. I don't need to mention. So useful energy 5 megajoule. With this we could establish a number how much CO2 you release from kilowatt hour of electricity produced if we are using this coal, this grade coal in a power plant, right, with the efficiency of 26%, 960. So, ma'am, do you agree with the number, or you have something else in mind for a coal-based power plant from the GIA reporting?
It's okay.
Yeah, so keep this number in mind. It's almost 900 grams of 900 kg of CO2 per megawatt hour of energy or useful energy. Similarly, let's take an example of natural gas. So natural gas is most of the time about 95% methane, remaining light hydrocarbons, and also CO2. Sometimes natural gas, it depends on the source of the natural gas. Sometimes gas will have a lot of CO2 associated with natural gas, so to remove it. But typically, this is the pipeline what we have in most of the country, also in India. That's the typical composition. So if we do the similar calculation here, you could see 0.962% is methane. That means 44 divided by 17. And I just put 1.05 here for sake of simplicity because we don't have methane. We also have methane. You could see 1.74%. So ideally, you would have done the calculation based on 96 times 44 divided by 17 plus 1.74 times 44 divided. What's the molecular weight of it? Sorry? 16 is methane. 30. C2H630. So ideally we would do the calculation based on each component, but for sake of simplicity, we put a number 1.05 because methane is also less than 2%. Now look at the heat release, it's 44.5 megajoule. So useful energy is 20 megajoule, and the CO2 intensity would be around 470 grams per kilowatt hour of power produced. We saw in the last slide we used 0.36, and in this slide we use 0.45. Because efficiency of a natural gas based power plant is usually higher. You have a lot of losses with coal as fuel, but natural gas or energy you can use more efficiently. It's a little bit higher in the efficiency. But that's not really making the difference from 900 to 470. That's not the efficiency. Yes, efficiency is helping, but you could say it's 470 grams per kilowatt hour. You can already say going from coal to natural gas is reducing the CO2 intensity. So reduce 1 kilowatt hour of coal, you are using 910. Remember how much? Yeah, 910. And if I replace coal to natural gas, I already reduced, producing same amount of power, I already reduced my CO2 emission by almost 50%. So there are a lot of fuels, not only coal, natural gas, but there are many other fuels industry, they use oil, they use diesel, fuel oil, heavy cuts from petroleum. I'll not go into detail for hydrogen now, but just to show the comparison, you could see here, coal is 910, we go to natural gas, it's 470, and the fuel oil, the heavy distillate from petroleum, diesel, they lie somewhere in between coal and natural gas. And natural gas is heavy, it's more carbon, heavy carbon. And just to show the comparison between natural gas and methane, methane is even lower. And if you burn hydrogen, I think there is no carbon release. So please consider a small blue thing as zero. What it means, as you go from coal is like no hydrogen here. So the C to H ratio, as you reduce your C to H ratio in your fuel, you will reduce your CO2 intensity. That's what I wanted to show here. So fuel oil, diesel, we're talking about maybe 70, 80, so even higher. So, we saw over the last 25 years we went up from 360 to 420. Now let's consider three scenarios. Please forgive me for this this mess up here. Something coming up later. But if you continue the business as usual, very soon we will go to 480. So 50% emission reduction will give us 425 in the next couple of years. But we want to go back to this temperature increase level to 1.C. It's very difficult. You cannot suddenly tell people stop using your bike and scooter and start coming to the bicycle. You can say, you can motivate them, and you can convince them to do that in Unity campus. It is very nice, and ask them to use bicycle going to the station. Business will continue. For sure. So, to come back to this 1.5 degree scenario, so IPCC, if I'm not wrong, maybe Dr. Kalpana correct me, Intergovernmental Panel on Climate Change. It's an apex body. All the countries have come together, discussed this issue, and they have set out some plans how we can go and address this problem. So they have pledged that they will go net zero by 2050. That means they means the Western countries. There is also a political angle in this one. So who has created the mess with the most responsibility to clean it up? So they have to lead it from front. They have to take more responsibility. And they have to do the majority of cleaning up. So they have pledged that they will go net zero, means they will go from coal up to the hydrogen. So not really hydrogen, but to the zero carbon energy sources. With this it will be net zero for them by 2050. Although India is not responsible for this 620, out of the 620, we were responsible for less than one. Very small amount. In terms of absolute number, but also in terms of per capita. Because we have a huge population, but still very less CO2 emitted. But to my happiness, to everybody's happiness, and all should be proud of this, India is marching ahead, not very far behind the Western countries. So we have pledged by 2070 we will also go net zero. So what we just saw, this small calculation, this is all CO2 intensity. This is also sometimes called as CO2 footprint. So what's the footprint? Exactly it's coming from. What's the amount of CO2 you are releasing? That's also called CO2 intensity, also the CO2 footprint. And just go on internet and see some plots here and there. You will see in today's world, the more CO2 footprint a country has or a society has, the more prosperous they are. So it's kind of somehow it's related, connected to sign of prosperity. The more energy you are using, the more rich you are. Somehow it's also true. If you compare what we use here in India is maybe 10 times more than what people use in East Europe. They are using 10 times more energy than us. The Western world, they are even talking about, even if we do go 2050 net zero, or let's say everybody by 2070 net zero, will not reverse the damage which has already been done. So to reverse the damage or to reduce the CO2 concentration in the atmosphere, we need to remove the CO2 from the atmosphere and put it back somewhere. So they're talking about negative emissions. At the moment we have positive emissions, almost 20 billion ton to the atmosphere. But beyond 2050, they are already talking about negative emissions. Yes, they will start not only they will stop emitting CO2, but they will also start capturing CO2 from atmosphere, thereby reducing the CO2 concentration in atmosphere. So that's the path society want to follow here, by 2040, 50 net zero, and after this even negative emission. And some of the let's say methods of forestation. So that's why everybody is talking about Kailas, so going net zero, or let's say using carbon-free energy sources and aggressively doing afforestation. So here you could see the CO2 emission of some of the countries I was already mentioning. Let's see where do we stand, 1.8, and where all these Western countries stand, 15, something like this, or almost 7-8 times. So that's the country perspective, but there's also a developed perspective. Here you could see that's the UK. Economy is going down, so energy consumption is going down. It's a little bit less. Here you could see the China, sudden increase. Sorry, you want to say something? Oh, sorry. Thanks for reminding. Sorry. So we are talking about, just to repeat on this slide, I will not go back, but just on this slide. Here you could see India, 1.8, and all these Western countries somewhere around 15. So, as we were discussing earlier, almost 8, 9, 10 times more energy intensive than us. So that's the country perspective, and this one is the plot showing this developing nations perspective. You could see UK coming down because last 5-10 years the economy is not doing so well, energy consumption is going down. Probably that's the United States, more or less stable, now going down because, so difference between this one and this one is, that's the consequence of their economy not performing well. That's the consequence of a lot of efforts the Americans have put in to reduce their CO2 emissions. So their graph is going down. And look at China, the China growth story everybody is familiar about. Suddenly from 2000, they almost reached the UK level, the Western level. And look at we humble Indians, somewhere here. But we also have our own growth story, so we are also going up, but not at that pace. Now imagine China was here 20 years back. There was not so much talk about CO2 emissions, that we have to reduce the CO2 emissions. And they were allowed to grow like this. Nobody put any pressure or any limit on them, and they released suddenly so much CO2. If you take this period and this period, their CO2 emissions is similar. So what they did in last 20 years, they did in last 100 years. So unchecked, uncapped, they were allowed to grow. And now suddenly we are on our growth story and people are telling us, please don't release CO2. So these two things are linked. So there's also a political, we'll try to stay on the technical parts, being engineer, but I just wanted to show there is also a political aspect of these things. So the debate of developed nation, developing nation, you develop based on, let's say, on this CO2 emitted, and now it's time for us, and you guys are telling us don't emit CO2. So I think similar graph you could see on this side, you could see the population, just to give you perspective. China, highly populated, India, similar population. And that's the CO2 per person emitted. And it's already also written here, so if you multiply this by this, then you know. And graphically to show that the best way would be the area. Visibly you could see at the moment most of the CO2 is coming from this guy. And this guy, we are also top 5 nowadays. Similarly, on this plot also you could see with the per capita income. Because this prosperity and per capita income and the CO2 emission, energy use, all these things are related, correlated. So developed society, the rich societies, somewhere here, they are on the higher side. So there is a trend. So less privilege, with the less GDP, they are also emitting less. So more you have, more you will spend, and most of the time you spend in dirty stuff, which emits CO2. So that's, we talk about the absolute CO2 emissions, right? Country-wise, we also saw the India perspective. And this one is showing where exactly the CO2 is coming from. So 20 billion or 25 billion tons CO2 per year, it's a huge number. Billion is 10 to the power 6 and ton is 1000 kg. So you could imagine, it's a huge number. Where exactly it's coming from? So majority is from power industry and other industrial combustions. So we saw Haber-Bosch process, that's one. Transportation. So within the transportation, it's also not just the private vehicles, but the air industry, the airlines. And can you imagine what would be the biggest contributor within the transportation? Which other transportation mode has very high CO2 emission? Sorry? Cargo ships, marine industry. Yeah, very good, thanks. So building is not a let's say significant number for us, but it's a big number for Western world because the climate is very cold and you have to supply a lot of domestic heating. So that's the world perspective, and here we see the India perspective. So here also we have most of our similar thing. Most is for the electricity, power production, other industrial combustion, and you already see that buildings is a smaller fraction for us in India. Transportation, although we have already, let's say, decommissioned the bullock carts, but our society is not so, let's say, intensive on private vehicles. So the number of cars per person, per capita is still much lower compared to the Western world. We still do not travel so much in plane, do not use so much. We do not have any waterways, so no shipping industry, no marine CO2 emission. That's why our transportation contribution is also much lower. There are some other sectors such as cement. So what we'll do in next 1 hour or so, if time allows for the lunch, we'll be looking at each sector one by one. and to not to spend 2 days or 3 days only on all the sectors. We'll limit ourselves only on the power industry, industrial combustion. Probably we'll talk about a few minutes on transportation as well. But majority will stay on the power industry and other industrial combustion. So where exactly all this electricity is coming at the moment? So here you could see, I tried to put everything on one slide, so world perspective and Indian perspective. As expected, we are more coal-based because we have a lot of coal resources. Western world, this one is for the whole world, the global, but a combination of developing economies and developed economies, they've already started to move away from the coal. So here you could see the coal fraction is almost 38% compared to almost 60% what we have. You could already also see the difference in renewables. Many countries, they also started earlier, they also had money to invest. We'll see in coming slides, going green is not cheap. It costs a lot of money. So they had the money, so they could invest more on renewables earlier. Our fraction is still low. But as on the hydrogen mission, on the renewable also, I must say we must be proud of what we have achieved in last 10 years or 15 years. India is the only country which has revised their targets. So countries, the government, they set their targets. So how much electricity we will replace from fossils to renewable. And proudly saying we have always revised our targets on the positive sides. So for example, I don't remember exactly the numbers, but for 2022 targets, they were achieved already in 2019. And 2030 targets were set at 5 times higher than what they were set earlier. So it's something really to be proud about. So we are not far behind the Western world. So I think coming back, business as usual will go up to 480 ppm. We need to reduce it, and beyond 2050, we also have to go to let's say negative emissions. So what's the need of the day? We already know we have to increase the share of these sources, and we have to reduce all these dirty fuels which are emitting a lot of CO2. So now enough of political and graphs and this. Let's work on, as engineer, let's work on some technical solutions. So typically that's how you do. You burn your fossil fuels. You use this energy for electricity production, consumption, transportation, or industrial use, and then you release the CO2 to atmosphere. So how we can reduce CO2 coming out from this box going to the atmosphere? So the first way is to reduce its uses. That could be by 2 ways. As I was saying earlier, by saying, okay, I'll not use my bike from today, so I'm not using any fuel, I reduce it to 0. But we all know that's not possible. So one way of reducing it is by increasing efficiency. So when this topic started on the World Forum, initial couple of years, the focus was mainly on increasing the efficiency. So nobody was talking about efficiencies in the plant before maybe 1990, 1995 or so. There was one period in 1970 in US. There was this oil embargo from the Middle Eastern countries, and suddenly they realized. Actually, what happened after the World War, everybody went to a peace mode, means we are not going to fight anymore, we'll live peacefully. And suddenly they found a lot of energy, a lot of oil and gas and everything in Middle East. And they started enjoying this. So focus was absolutely not on efficiency. So if you have a car engine running, it's running. It was absolutely normal. Leave your car engine running. In Scandinavian countries, probably you know, but maybe not now, where you have temperatures like -20 or even lower. 20, 30 years back, they told me it was absolutely normal to leave your car on for the whole night, because next morning it will not start, and nobody was caring about how much fuel they will burn. They just leave it on. Nobody was worried about CO2 and other emissions, but you cannot think about those things now. So increase efficiency. So they came up with the idea to keep their engines warm by using electric batteries. So innovation came up because of the need. And as I was saying, in 1970, the first need came when the oil embargo from Middle Eastern countries really put Western world under pressure. There were long queues. If you go to the YouTube, you will see 1970s there were long queues on the petrol station. That was really unheard for Western people. So yes, once again, increasing efficiency, that was a focus in the early years, but still continues to be so in developing countries like India and China. So wherever you can increase the efficiency, you could reduce CO2 emission for the same energy output. The next one would be replace it. We already saw in earlier slides, if we go from coal-based power production to natural gas-based power production, we already reduced CO2 emission by 50%. So the next step would be replace it. And if we move even further from natural gas, and if we use hydrogen, it's like zero carbon, so carbon-free, so low carbon to carbon-free energy sources. But as I said earlier, this going green or going from coal to natural gas is expensive. Similarly, from natural gas to hydrogen, it's even more expensive. Some people from hydrogen business, they know the cost difference between hydrogen and other fuels, so it's not cheap. So intermittent solution could also be, what else you can do? You continue your business as usual, increase the efficiency as much as possible, go to low carbon fuels, practically or economically possible as much. And whatever CO2 is coming out, you capture this and don't let it go to the atmosphere, but you sequester it. So by sequestration, I mean you can have your CO2 fixed permanently somewhere in the geological structures, formations. One way is enhanced oil recovery, probably you have already heard about. So when you recover oil from oil wells, so slowly the pressure reduces in this well, and at one point it's not economical anymore to release or remove this oil. So normally pressure is high in these oil wells, and you simply tap it, open the valve, or crude oil is coming out. But as time goes, you remove a lot of oil from it, pressure goes down in this reservoir, and you have very less oil coming in. And at one point, it's so expensive to remove it that you cannot have, there is no business case. So you just leave it. But still there is some oil there. So what people were doing 10 years ago, they capture CO2, pressurize it, and put it in this oil, and let the oil come out. So you enhance the recovery of oil. So oil wells which people earlier suspended or left alone, they came back with the CO2, high pressure CO2, put it in these wells, and then remove oil. So you have solved two problems. One is fix the CO2, and that also pays off by having some additional oil. But the debate is the amount of CO2 you fix in this oil, similar amount of CO2 in form of crude oil you are removing again. So that's not a permanent solution. It's just an intermediate solution. Enhancing from going from coal to hydrogen. Somehow it must be economically supported. So that's one way you capture CO2. What I want to say, you continue your business as best possible with the best efficiency, with the best possible economically possible low carbon fuels like natural gas, whatever CO2 still comes out, we take it and sequester it somewhere. So enhanced oil recovery is one example, but there are other ways. There are geological formation where you do not have any oil or anything coming out, you just put it there. So that's one way, sequestration. Sorry. Another way is to have the CO2, instead of sequestering it somewhere, you can use it in industrial processes somewhere and produce products. So one example of this, or maybe I'll let you tell me any example of CO2 use in industry. Industrial use of CO2 application. Remember anything?
Beverages.
Sorry?
Beverages.
Beverages. I was about to say everybody in this room is drinking Coca-Cola, but nobody is saying beverages. Yes, yes. Nowadays CO2 is also used industrially as refrigerant, replacing ammonia because of safety. So although the GWP is higher for CO2, it's a greenhouse gas, but as a refrigerant is much better than ammonia. So traditionally we always had ammonia as refrigerant used in industry, but because of the safety aspects and other issues, CO2 is replacing ammonia. But market is not so much. So amount of CO2, 20 billion tons, 30 billion tons annually would be released. The refrigerant market would be not even 10,000 tons a year. So it's a very small one. But वो कहते हैं ना बूंद बूंद करके घड़ा भरता है. So everything counts. Every step helps. So that's one way. Either you capture all the CO2 and sequester it somewhere, or you put it back. But the bad thing about this route is ultimately you are again releasing the CO2 back to the atmosphere. Recently, traditionally methanol is used for and traditionally it is produced via natural gas. Last 5 years people started talking about we cannot directly go from low carbon or coal and oil and this to hydrogen, so we'll continue with natural gas. It's not as clean as hydrogen, but it's also not as dirty as coal. So we'll continue with methane, and whatever CO2 comes out, we will take it, and then we will have hydrogen. We'll see in coming slides, but this captured CO2 will be combined with hydrogen, but this hydrogen will be the renewable hydrogen from electrolyzer, and methanol is produced. But coming back to this, the drawback of this step is, or this route is, you produce methanol from maybe green hydrogen and CO2, but somewhere this methanol is used, and wherever you use it, your CO2 is again released. So we'll see the policy aspects in coming slides, but governments and regulators, they also understand you cannot have a knee-jerk change, disruptive change. You cannot tell industry that please stop using coal and natural gas, everything now it's only renewable power and only hydrogen you have to use. So they want to have this transition slowly. When we say slowly means 10-15 years. So in regulatory terms, this route is still allowed, but only for next 10 years or so. By 2040, companies, I won't say not allowed, but they will not be encouraged to use this route or this utilization, because ultimately, once again, CO2 will be released, so it's not a permanent solution. So I think this we already covered up in the last slide. Okay, on the combustion side, there could be two ways, post-combustion and pre-combustion. So you let the business run as usual, and you just bring a tail end unit on your flue gas stack. So for an example, for the power production, you burn coal, you produce your electricity via the steam cycle or gas turbine, whatever, and finally your flue gas coming to the stack. Instead of sending it to stack, you send it to a capture unit and you capture the CO2 and send it to the storage site, which could be enhanced oil recovery or depleted gas well or any other geological formations. Or you go to the CCU route, utilization. But there could also be some pre-combustion techniques or technologies. So one is oxy-combustion. For example, when we burn fuel or coal, in this case using air, we also have a lot of nitrogen coming in. So one aspect of or drawback of nitrogen we just discussed a few minutes ago is this NOx. But another one is this nitrogen is inert and just flowing from point A to point B doing nothing. But while going out to the atmosphere, it's taking a lot of energy with. So you could increase your combustion efficiency drastically by replacing air with oxygen. So relating what I said earlier, going green is not clean. Producing oxygen from air will also cost you something. So you will have few percent of increase in efficiency, but oxygen cost is significant. So producing oxygen from air will cost a lot. So that's wanted to relate once again. Going or getting clean or reducing CO2 emission is not cheap. It will always cost you something because there is no off-taker of CO2. There is nobody who will say, I'll buy your CO2. Or you treat your fuel. So what people are also doing, they take the natural gas and before combustion, they do some treatment and increase the CH ratio. So they reduce the carbon content, overall carbon content of the fuel. So that's another way. So pre-combustion, post-combustion, that's the basic difference is you let your business run as usual, like in power plant, and whatever flue gas you normally send to stack, you take it and put a tail end solution, and pre-combustion is before combusting your fuel, you do some treatment, you do some tricks so that you have less CO2. So that's also very common terms, just wanted to make you familiar. So I think we repeated it 3-4 times, getting better is expensive, it's always normal. So similar composition of natural gas, what we used few minutes ago. Similar calculation will give me the electricity price of. Hello, it's working. Yeah, now it's working. So similar calculation gives me a power price of 170 euro per megawatt hour. So if I continue with natural gas, I'm producing at 95. And if people are telling me you are doing bad things, you are emitting a lot of CO2, please stop it, use solar panels. My production price is 174. So the difference is 79 euro. Yeah, 79 euro per megawatt hour. Right. We'll come to this. Who's going to pay this 79 euro? So just to be nice, end of the day, everything turns around money. Yeah? So we'll see in coming days how government is promoting industries, how this 79 euro is being offsetted. But let's limit our discussion on CO2 cost. So we already saw for this natural gas, it's 470. For this, it's 0 because we are not using any carbon, any fuel which has carbon or which results into any CO2 emission. So going from this to this, we avoided 470 kg of CO2, but we have to pay 79 euro. So that's my CO2 cost or CO2 avoidance cost, somewhere around 167 euro per ton. Actually, these numbers are based on assumptions. So if you go somewhere, the numbers will be a little bit different here and there. But idea here is to give you the feeling how these calculations are done and what's the order of magnitude we are talking about. So somewhere around 170 euro per ton will cost going from dirty to clean. Okay, so if as a power plant operator, if nobody is going to pay this 79 euro, I'll simply transfer this cost to my consumers. So I'll start selling the electricity at much higher rate, and at the end of the day, consumers are we all. Now, why? And the direct effect of this price increase would be reduction in the consumption. So that's also not good for the business. So if you increase the price, the consumption will go down. That's not good for the business. So why will producers stop using natural gas? If nobody is paying, and I know if I increase the price, my sales are going down. So I'll simply throw all the panels away and go back to natural gas and start producing at how much? 94 euro per megawatt hour, so that I keep my customer base intact. So just because it's nice, clean, green, nobody will do that, because at the end of the day somebody has to pay this 80 euro, 79 euro. So as I said, in business everything should be supported by business case. There must be a business case. It must make economic sense. So now here comes the way government is. So first of all, there is a global consensus between the academics, scientists, and they managed, or they succeeded in convincing governments that this is a serious issue and something needs to be done. So government started to support or frame policies in a way that industry will move from carbon intensive energy sources to low carbon or zero carbon energy sources. So emission trading scheme is one example. We'll talk about this in a little bit detail. So at least in Europe, how it works, Dr. Kalpana, please feel free to interrupt and correct and add any time. She is also an expert on this. So what they do in Europe, or what they did for last 15 years, 20 years in Europe, is the government assigns certain number of CO2 emission allowance. So allowance means as an industry or as an operator, I'm allowed to emit X number of, or let's say X tons of CO2 annually. So that's the allowance, right? Yeah. So, and how these allowances were let's say decided, how the amount of the CO2 was decided. That was decided based on the BAT, the best available technology. So, as an industrialist or operator, power plant operator, I'm forced first of all to use the best available technology. That means increase the efficiency up to the maximum, so that CO2 emissions are already low. And then based on the countries, some industries were given allowances, that you are allowed to emit certain number of CO2 tons per year. Now if government says this is the amount or this is the number you are allowed to emit every year, CO2 emission will not come down. So what they will do, they will not increase their capacity, but they will also not reduce the CO2 emission. They will just continue as usual. So very nice, we have some allowances and we will emit this. We will not grow, or business will not grow, but we will also not die. So they will continue like this. So what governments decided is that they said the allowances will go down year by year. Right? So for an example, in Europe, the power industry do not get any allowance. So it doesn't mean that they are not allowed to operate. So they still operate, but they do not have any allowance. Means they are forced to do something with their CO2. So they have two choices: either continue their power plant, operation of their power plant, emit CO2, and in case face penalty. So penalties are somewhere around 130, 140 euros per ton. Or do CO2 sequestration, capture and sequestration. So that's the only two options they have. Or diversify to renewable power or some other energy sources. So I think in India also we have already seen the thermal power plants tenders are cancelled because the renewable power or the solar power price has gone down so much. No major power plant, thermal power plant is announced in last couple of years in India, even in India. So there is another reason we are blessed with the more solar. सूरज का बहुत आशीर्वाद है हम लोग. So we are blessed with that. But yes, in Europe there are no allowances anymore for power industry because government thinks that there is an option for power production moving from coal to renewable. But there are some industry, there are no solutions, and cement is one of the examples. So as we were discussing earlier, cement is limestone. What could be the replacement of cement, if you can think about? If we say there is no cement today, from tomorrow, what could be the replacement? You can build your houses with the wood. That's also, let's say, going in the negative, bad direction. But you could, there are some replacement. But for the houses, but not for the bridges. You cannot build bridges without cement. So cement is a good example of industries where absolutely there are no other choices available. Until unless they found a replacement for limestone, as long as you want to produce cement, you need limestone. As long as you are using limestone, you are releasing CO2. So there is no choice for. So these industries are called hard to abate industries. So electricity you can abate, removing, or let's say you stop using coal, natural gas and other carbon intensive fuels to renewable power where you do not have any carbon in the chain. But cement is one, as I said, where you cannot do anything. So carbon capture is the only solution here. So in the earlier years of this ETC or ETS, what governments in Europe allowed is, for an example, as a company in Europe, I'm given X tons of allowances, right? And I'm releasing X plus 10. So I will have penalty on 10 tons normally in the normal case. But if I can prove that I have executed a project in China or in India or in Bangladesh or some other country, where I reduce CO2 emission by 10, then I will not have any penalty. Correct? That was the way early days of the ETS, European trading scheme. So CO2 avoided was allowed, but nowadays they have absolutely banned it also. So there is no matter how good you do in some other countries, how much CO2 you reduce by investing in projects in some other countries, your allowances will not be adjusted anymore. So in European countries, they are absolutely forced to do something, because in the early years, even today, I will not say that for India, but for other countries, efficiency is still very low for some sectors. So it's very easy. If I have to reduce, let's say, 10 tons of CO2, my emissions by 10 tons of CO2, I simply go to a power plant or to an industry. I do a small project, a small investment, increase the efficiency, and suddenly I have, instead of 10, 20 tons less CO2. So earlier it was allowed, but now they simply stop it. So there were many, or still there are many such schemes. And EU, the European Commission, they came up with this ETS, European ETS. It was launched in 2005, as we already discussed, to push industry going from low to zero carbon. So it's built upon the cap and trade mechanism. What it means is, I tell somebody you are allowed to only emit X number of tons of CO2. But let's say there are two companies in Europe A is doing nothing and B is investing heavily on carbon capture. So they had an allowance of X tons, but now they are emitting only X minus 5. So what they can do, they can take these certificates or this allowance and sell it to somebody else. And somebody might decide, I'm not in the mood to invest in carbon capture, I'll just go and buy the certificates. So they buy these certificates, and with this, whatever difference additional CO2 they are emitting, they can show to the government or to EU that we bought this. It's just like instead of investing in their plant and capturing CO2 or reducing CO2 emission, you simply go to the market and buy these certificates and have your commitment done. So cap, as I said, cap on how much emission is allowed, trade in the open market like the stock market. And from 2005 till 2010, I think the cap was not decreasing. That was the phase 1 of EU ETS. But since 2010, this cap is slowly decreasing. As I said earlier, there is no allowances anymore for the power industry. Aviation industry allowance will be brought to zero in 2026. So they have to go from conventional ATF, aviation turbine fuel to sustainable aviation fuel, or do something else, buy credits or pay penalties. We said some industry will continue to receive allowance, and cement is one example. There is no other way, and they go to the EU and say, we can't do anything. Either you give us either you finance heavily on research, that people, academic researchers can come, scientists can come up with alternative materials, then as I said, those are, let's say, we normally call them hard to abate industry. It's not easy to. So here, try to explain this with an example. So for example, if you are a power plant operator operating a 500 megawatt natural gas-based power plant, yearly you are producing 4,000 gigawatt hour of power, right? And with the number what we had earlier in mind, 470, that's the amount of CO2 you are releasing every year, right? In 2005, before the ETS, right? So suddenly ETS came in, and in 2010 they told you are allowed only 1.5 tons per hour. So now you have two options: either reduce the capacity of your power production or plant to maybe, I don't know, 420, 430. So in the same ratio, 500 is for 1.8, 420 would be for 1.5, something like this. And then that's fine. But you have an installed capacity of 500 megawatt and you are producing only 420. That's not good. So if you have to make maximum use of your assets, whatever you have invested, or your power price. Otherwise, your power price will go up. Or you can go out to market and buy the certificates for 0.3 tons. You continue operating at 500 megawatt. You continue releasing at 1.8. And I have the allowances for 1.5. I go to the market, pay for these certificates for 0.3, and now I can show you that okay, 1.5 you allowed me, and for 0.3 these are the certificates. Right? Cost burden, but at least I can continue to operate at 500 megawatt. Right? Now in 2020 compared to 2010, it will be, so let's assume in 2010 the carbon price was, the certificate price was only $20 or 20 euro per ton. Today it's trading at somewhere around 70 euro per ton. And companies are expecting that this will go up to 150 or even 200 euro per ton by 2030. Because it's a typical supply-demand thing. What EU is doing, they are closing the tap on allowances. So if there are no allowances, there are no certificates to trade, there is no demand, there is no supply, demand is very high, suddenly the price will go up. So that's what they are thinking, that the price will go up to 200, 150, 200 euro per ton by 2030. So in 2010, for our example, let's say the price was only 20 euro per ton. I also have to buy only for 0.3 because I have a huge amount of allowance. Now suddenly what's happening? This is going down, 1.5 is going down. That means I have to buy for more. Slowly, the allowances given to industry is coming down. That means in the market it's very difficult to buy these certificates. So price is also going up, and the amount of certificates I need to buy is also going up. So suddenly I had only, let's say, 6 here, 20 times 0.3, and if this 0.3 becomes maybe 1 and this 20 becomes 100, I'm now at 100. So 6 to 100 and 16 times more expensive. So that's the idea of the approach EU is following. Slowly dry up all the allowances from the market. With this the price will go up and the industry will be forced to do something. So it's going up and up and up, and there will be a point where it will not make any economic sense to operate a power plant within natural gas. So we saw in previous slides that for 1 megawatt hour it was somewhere around 80 euros. So if I have to pay for 1 megawatt hour electricity equivalent to CO2, if I have to pay more than 80, I will not do, because I have a solution. I'll simply shut down the plant and install the solar PVs. So at certain point they want to squeeze so much, governments, that at certain points industry will be forced to go from CO2 intensive sources to low or zero carbon energy sources. So offsetting in the initial years they allowed, because this was the transition phase, to avoid this knee-jerk. You cannot simply go and tell them stop doing what you are doing for the last 20 years. That's the, we call it business inertia. Inertia, that's also personal inertia. There's a societal inertia. You really need to be convinced of change, whatever you have been doing for years. In industry also, in the plant also, people are, no, I've been doing this for like this for 20 years. And so, allows industry, society to smoothly go. So this knee-jerk thing, what we talked about, carbon neutral to zero, and reducing greenhouse gases emission costs a lot. Offsetting allows to cover partly the costs. Till 2005 to 2010 period, a lot of companies misuse it, this offsetting clause. So now they came up with the airtight mechanism, really stop awarding allowances for many industries. They removed the offsetting clause. So, yeah, they're coming up with airtight mechanisms so that goals can be achieved. So that's basically the European ETS we talked about in phase 1, phase 2, phase 3. That was from 2005 to 2010, and 14, and we already entered the 4. And now EU is asking all the companies, the groups, to surrender their certificates what they earlier issued to them. So we talked about this many times. No international offsetting is allowed anymore. So there's also a political aspect on this side. What they are trying to do is also protect the European industries. Since China, we saw that last 20 years China has become the manufacturing hub of the world. So slowly European industry is also dying. So the level of research and innovation was going down. And with this, they are trying to push back the innovation to EU and bring back the industrial manufacturing back to Europe. So there is some political aspect also of all those things. So as on all other fronts like solar, PV, hydrogen and other things, the Indians are also not far behind. We have our own trading mechanism. I think it's still not enforced or it's not in place, but that's the draft what I found or what I saw. So Paris Agreement we entered in 2016. We committed initially 35% reduction based on 2005 emission by 2030. I was telling earlier that it's a proud thing for us. We always revise our targets, but in the positive direction, not in the negative direction. So for 2030 we said 35%, we already revised it to 45%. So it's more or less based on European ETS. I have a link when we had the slides here. You can have the detail, you can have a detailed look on it. So compliance and offset. Compliance. Making a policy is one thing, but making people to comply to these policies is one thing. And there, reporting is one of the most important things. And we have Dr. Kalpana here, and she is an expert on.
Reporting is compulsory in India.
Yeah.
GRI worldwide.
Yeah. So, if you do not have these reporting procedures, I'm just talking in layman language, without going into details. But if you do not have this standard approach or standards to report the greenhouse gas emissions, there is always a way, you can trick. No, my leakage is not an emission. My emission should be, what I'm trying to say is it's very easy for companies to make government fool, to report lower CO2 emissions or lower emissions than what they actually are doing. So that's why reporting is so important, and that's what the governments are doing. They are setting down or putting down all the reporting procedure, what needs to be accounted, what needs to be excluded. I think we are still in initial phase.
Scope and scope 2 is compulsory.
Sorry?
Scope and scope 2 is compulsory, not scope 3.
Not scope 3. So, but with this trading mechanism in India, we are in
carbon
still.
trading is still yet to enforce. I mean, like just last year it has been announced.
Proposed and
Trading,
drafted.
yeah, but not started yet.
Trading has not started, so it's still in initial phase to be watched how smooth and effective the scheme will be. But India has one advantage. We have a lot to learn from the European ETS. So I'm pretty sure this scheme will be much better than the ETS. Whatever mistake they did, we could learn and make our scheme much better. So we are talking till now, till here, till current thing. We already so far talked about how we can reduce CO2 emission. We go from coal to gas, and that's what you also can see in this graph. No, not probably here, because somewhere around 1970, 80, when this thing came up, slowly they moved to gas. It's also combined with the discovery of gas in the Middle East. So what we means world, the whole society has achieved so far. You could see how the coal was peaked here somewhere around 2012-13. As I said, last 2-3 years, there are no thermal power plant announced, big thermal power plants announced here in India. Forget about in EU or Western world. So the coal is already going down. Target is to go zero by 2070. One can ask who will be emitting CO2 via coal, who will be using. So there are these Western countries, and there are developing nations like us, and there are also countries or continents like Africa. So it's difficult to convince those countries or bring them on board. So there will still be some emissions, continued emissions of CO2 via these things. Nuclear is an interesting case. So normally they say conventional and non-conventional energy sources. So conventional we say coal, oil, gas, and in non-conventional all these things come from offshore, onshore, solar, hydro, nuclear also. But when we say renewable, poor nuclear is excluded. because although it's carbon free, because in nuclear you do not have any carbon CO2 emission, it's just the nuclear energy what you use to convert to thermal energy of steam and then generate electricity as you do in a typical coal-based power plant. But conventional, that's the difference between conventional, non-conventional. When we say non-conventional, we talk about all this, but when we say renewables, we only talk about these. Because nuclear, although it's zero carbon, it's unconventional, non-conventional, but it's not renewable. It will be finished one day. So that's one. So solar absolutely exploded beyond 2020. Let's see the biggest one. 2020 is really going high and high. So 2005, 2000 coal started to go down, replaced by gas fired. First of all, the gas going up, coal going down, clear decline of coal beyond 2015. Although the benefit of wind is similar to solar, but somehow the wind industry is left behind in this story. Solar has really exploded, but wind not the same way. We'll see in coming slides what are the issues with the wind industry, although it also generates clean power like solar. And nuclear shows sustained share due to the mixed opinion. Although it is considered the as clean energy source as solar, onshore, offshore. But now we come to the scope 1, 2, 3 emission. So with the solar, it's there are no scope 1. I'll define it later, but briefly speaking, solar one is scope 1 is the emission what you have within your battery limit or within your plant, direct CO2 emission. Scope 2 is related to all the utilities you produce, use electricity in your plant. So all the utility related CO2 emissions, those are the scope 2. And scope 3 is all the CO2 emissions associated with transportation or bringing all the feedstock to your plant. That's correct?
Yeah, upstream, downstream.
Upstream, downstream, all those. So within your plant, that's scope 1. Within your plant, all the utilities you use, that's scope 2. And beyond, everything else is scope 3.
What is in between oil fired and gas fired?
Green one.
This one?
Blue, yeah.
This one? This is gas fired.
Oil
This one? This is hydro. You're talking about this one?
Yeah.
Yes.
Some thick
Just
line.
below the
thick
light
line.
green.
Yeah, below the green.
This one? This one?
Yeah.
This is gas fired.
This.
Natural gas.
Gas
The purple.
I'm colorblind.
Okay.
Let's use this one. Coal? Natural gas? Or,
and then next one?
yeah, next one I also do not remember.
Coal
Oil fire.
Oil fire.
Yes. This one is nuclear. Yeah. Hydro, solar, and then onshore, offshore. So yes, society is making progress beyond 2020. You see, solar. I was talking about the nuclear. So there's a mixed opinion for nuclear. After this disaster in Japan, people suddenly started talking about, oh, it's all very clean, but we don't want to do anything with nuclear. So that's the apprehension people have with the nuclear, although it's very clean. But then there are some other countries, even within the EU, there are countries like Germany who have already stopped their last nuclear plant. But just across the border in France, they have their power, almost 50% of power is coming from nuclear. And they say we will continue to do so. So it's a mixed opinion, even in the similar, let's say, society where they have alignment on most of the issues. But on this issue, there are still a lot of differences in opinions. So that's an interesting case. And in India, I think we are going nuclear as much as possible. So there are big plans for us to install nuclear power. Okay. Yeah, let's try to do the same, take the same example and do some calculations here. You use your carbon intensive energy source, produce electricity, and then you release CO2 to atmosphere, and that's the one similar. If you have coal base, and if you go to natural gas, you take air, you burn it, you generate steam, and you produce electricity. So scope 1, 2, 3, we already said. Going back to this example, for 500 megawatt power plant, you have only 1.8 million tons of CO2 per year. That's my scope 1. But during this process, I use a lot of cooling water, and this cooling water is not the cooling the water, the river water what I'm taking. Even if I'm taking river water, I have to pump it. So I'm using some electricity. So generally, you have to put in a lot of power to produce the cooling water. So all the CO2 emissions
cooling tower.
It's coming from cooling tower, for example, and you need power to run your fans. So a lot of electricity goes in, and this electricity is also generated somewhere in the coal-based power plant, and there you are also releasing CO2. So you are not releasing CO2 only this one within your plant, this 1.8, but somewhere else also. So scope 1 is the CO2 what we are releasing in our plant, and scope 2 would be all the CO2 which is related to the utility.
Indirect emission.
Indirect emission, but related to utility, used within the plant. Now if I go back, as you were saying, a lot of emissions or let's say energy used to transport this energy, natural gas. So anything beyond, as you said, beyond your plant, everything is scope 3. So
that is also indirect.
That's also indirect. Yeah. So if we when we are doing calculation in earlier slides, what's my coal? I burn this much coal. That's my LHV. That's my carbon molecular weight. That's the CO2. But actually, it's not only this CO2, but it's a lot of other sources of CO2 emission. So that's what they define it as scope 1, 2, 3. And if you wouldn't take into account all of this, we'll report 1.8. But actually, it's 1.8, 0.15, 0.5, based on some assumptions. So my total scope 1, 2, 3 emission would be, would be 2.45 instead of 1.8. Now the CO2 footprint, I think this we already did, but let's take another example and then try to implement these calculations to calculate CO2 footprint. We did it for the power production, natural gas base, it's around 470 kg per megawatt of per kilowatt hour of electricity. But that was for the electricity. How we do it for the products. Right? So let's take an example of producing hydrogen, conventional way of producing hydrogen from natural gas. So you have steam methane reforming. We'll be spending 1.5 hours only on this part tomorrow. But those are the 3 basic equations: steam methane reforming, and shift reaction, water gas shift reaction, and the direct reforming. Altogether, without going into detailed calculations also, we start with natural gas, we end up somewhere producing 70% hydrogen, and the remaining goes to CO and CO2. Right? So basically what we are doing, we are producing 6.6 kg of hydrogen, 8.7 kg of CO, and CO2 is let's say unwanted product. Now, once it was very easy to allocate your CO2 emissions if you have only one product. What I want to show here is, if you have 2 products, how you will allocate your CO2. I can go in the market and say, whatever CO2 is released, I say it's with the hydrogen, so I will simply say 6.6 divided, I think I have it on another slide. No. So what I will do, I can say 6.6 divided by 45.6. That's my CO2 footprint for hydrogen. But actually, I am producing CO also, carbon monoxide. So generally, SMR plants, they produce sometimes pure hydrogen, but if you have a customer for carbon monoxide offtake, they also produce CO. So without doing this CO shift reaction. So how do you allocate your total CO2 to your two products? So one way, normally, specific heat, I remember, so specific heat of each component. If you have a mixture, how you will calculate the specific heat of this mixture? We simply do it with the mass composition, mass composition. But can we do that here? We can say we have 6.6 plus 8.7, which is how much? 15.3 kg, so 6.6 divided 15.3, which is 42%. So I say 42% of my CO2 is for hydrogen and remaining is for CO. But that's not the way, because energy you put in is going to end up in hydrogen and CO based on the energy. So that's the way, that's the actual way of allocating your CO2 footprint if you have more products. So you look at what's the energy content of your product, and based on this, like we are doing, we are saying we do with the CP specific heat based on mass composition. Here you do that based on energy composition. So you say this is my total energy out. That's 6.6 times 120. That's the LHV of hydrogen. That's the LHV of CO. So almost how much is this? Maybe 90%, if I'm not wrong. Yeah, 85, 90%. So 90% of my energy is going here. But weight-wise, this is 42%. So if I do based on the weight, I will say 42% of my CO2 is with hydrogen, associated with hydrogen. But in reality, 90% of my CO2 is allocated to hydrogen. So that's the way you report for CO2 footprint if you have more than one product. Is that correct, Dr. Kalpana?
Yeah. In India, we do carbon footprint, CO2.
Carbon footprint, yeah. So I wanted to be very specific. Actually, carbon is CO2.
India, carbon footprint, carbon market, carbon trading, it's all about that.
Yeah, it's all about that. Which is actually true because...
Yeah, but we use the unit of tons of CO2.
Tons of CO2, exactly.
Exactly. We all calculate in tons of
CO2,
ultimately.
Here I wanted to keep it simple. Related with the calculations, stoichiometric calculations.
Ultimately, we go for tons of CO2 only.
So that's how we will report. For the hydrogen, I have this 90% energy. So I will say that's the kg of CO2. That was my total CO2. So 0.9 multiplied by this. That's my CO2, let's say, footprint of my hydrogen product. And that's for my CO product. So sometimes you also you assign one as your main product and another one as a byproduct. So for the byproduct, you can also say your CO2 footprint in terms of main product also. So you can say CO2 footprint of my CO production of carbon monoxide is 0.7 kg CO2 per kg hydrogen. But you have to be very specific. Or you simply say 0.5 kg CO2 per kg product, which is CO. So, as I said, we'll look in this hydrogen manufacturing process tomorrow in detail. But generally, a SMR plant will also produce a lot of steam because SMR is an energy intensive process. So you have a lot of waste energy, and even after doing a lot of heat integration, you will not be able to use all the energy within your process. You end up producing some steam, some byproduction of steam. So let's extend the same example to the next level. We stop here. I think I had only two slides. Shall I? Just 2 slides. I requested and Dr. Shende agreed. Sorry, between you guys. Yeah, but basically, let's assume if you have 19 kg of steel, But if we apply the same principle, steam has no heating value, because it's not a fuel. If you cannot burn steam, so we cannot apply the same methodology if we have steam. But still, there is some energy going into the steam. So for such scenarios, for steam, what we do is normally we see for the H2 and CO we took the LHV, and for steam we take the enthalpy. So with this we say this much energy is going to H2, this much energy is going to CO, and this much energy is going to the steam. And similarly, we just extended it for the steam as well. We do for hydrogen and CO earlier without assuming no steam co-production, but now we have steam as well, and that's how we do the same. Look at the jump whole head, and that's what they call energy transition. Within 10 years, 20 years, 30 years, we suddenly move from one source to another source. That was the first one, and the next one came somewhere around this period when the oil was discovered. This was the first one with coal, and then suddenly somewhere around 1910, oil once again was discovered much earlier, but it was not started as a major until early 1900s. Then here also you could see how this color is for oil, how this should be during this period. That was the second energy transition. And now we are witnessing, we are today talking about actually in reality the third energy transition, but most of the people think it's a new term, energy transition. I think we saw this slide earlier, no, not yet. And we saw some issues associated with the carbon intensive tubes. Here on this slide you can see that that's associated with the air pollution using different energy sources. Once again, the area of the triangle is absolutely no that's electricity produced, that's per unit of electricity. So coal, as you all know, it's not only CO2 is sort of this GWP, but burning coal also results into several other pollutants, SOx, NOx, particulate matter. So as you go cleaner, it's also safer, you can say safer or healthier. This we already saw. So need of the day or call of the day is to go from higher C2X ratio to low to CX ratio. On this end we have infinity, on this end we have almost zero. I'll skip this slide. We already saw where this energy is coming from. Still coal is being shared between the gas and the remaining oil and some other sources. And you could see the renewable or the clean energy sources still doesn't make up so much in the complete energy mix. Yeah, electricity. So we said where this CO2 emission is coming from, majority is from electricity. That's all about electricity. Everybody thinks that electricity was discovered somewhere into 1800s. Inherent advantage transferred by cable. There's no transfer of matter or material, and it suddenly took over huge amount of energy production and energy use after its invention. So once again we'll look into different electricity generation. So this we already talked about. We burn fuel in the boiler. It's the simplest form of power plant. We burn fuel in the boiler. Can somebody tell me why we cannot have, why do we have to condense the steam after the turbine? So we have steam here, steam is coming out, and then we condense it somewhere here. So normally, a lot of energy content of steam is basically from its latent heat, from measured for 1 kg for atmospheric pressure, it is somewhere around 2100 kJ/s. But if you start condensing steam in the turbine, sudden phase change will damage the blades. And you still do not have an existing unit which can support condensation of steam inside. So, although steam has very good properties, it's non-toxic, non-flammable, non-corrosive, and can carry a lot of energy. So energy density is very high. You can put in a lot of energy in 1 kg of steam or water. That's a typical, just wanted to show a typical thermal power plant, how you produce it, the electricity. So some mass balance and energy balance calculation, we put in 30 megawatt fuel based on LHV. Only 12 megawatt is carried out.
इसमें ये पहले चला
इसमें ऑडियो ले रहा है ऑडियो इसमें ले रहा है कैमरा maximum amount of energy content of the steam
ऑडियो के लिए चालू कर दे
phase change.
Correct.
And if we are not changing the phase, we are losing a lot of energy. You cannot have this steam going back to the boiler, so you have to condense it and then generate once again the steam. So a lot of energy is lost here in this condenser. So basically you flow cooling water inside the condenser, and then ultimately this cooling water, as I said, goes to the cooling tower. Energy is lost to the atmosphere. Another energy loss will be you burn your fuel, but you can extract energy from this flue gas up to a certain point. So let's say, for example, 170, 180 degrees. So that's the amount of stack losses. So there are two losses here. So one is here and one here going to the cooling tower. So typical, just wanted to give feeling and typical numbers for power generation using coal. So as we said, maximum amount of energy content of the steam is in its latent heat, and we already agreed, or we already said, we cannot condense it within the turbine. But what we can do, if we generate steam at higher temperature, so let's say this energy content of the steam going to the turbine is high, then probably fractionally we can reduce the losses. So we transfer more energy at higher temperature, and that's what I'm showing here. So this is what goes into the turbine. Let's say this is the base case, and this is what comes out of the turbine, and the liquid fraction is 1. Typically flue gas come in and out, it's somewhere around 93, the efficiency. That means when I say 93% is what goes here as the fuel LHV, and minus what comes out, this is what is going to the turbine. That's something else, what you are using from the turbine, that's something else. But just purely on the flue gas side, you can have 92-93% efficiency. Here, in this example, you could see 30 as the fuel value we are putting in, and 3 is lost, so efficiency is 90%. Just from this point to this point. But out of this 90, we are only using 50 here. Is it 50? No, even lower. So 27 is coming in, 15 is a little bit higher than 50. Ultimately 12 divided 30, that's the 40% efficiency. So just to give some feeling how you can optimize it, how you can increase the efficiency. Always, for all the cases, let's say flue gas in, out, I'm with 93% efficiency. Base case, I generate steam at whatever temperature, whatever pressure, but I superheat it up to 400 degree. I'm coming out at 110 degree. Liquid fraction is 1. Steam turbine in and out, that means it's 90%. But as we said, we cannot have liquid fraction 1 from the turbine. We cannot have condensation within the turbine. So that's not the reality. But just to give you a feeling, one way of increasing efficiency would be if I can reduce the temperature at the outlet of the turbine. So if I go from 110 to 70, that means within the turbine I am extracting more energy. That can increase my efficiency in the turbine. Efficiency will go up. But this variation is just to show effect of this variation, right? These two cases. But reality is this: we cannot have condensation, so the liquid fraction coming out from the turbine will be 0. Right? And then look at the efficiency, overall efficiency, 42%. Because within the turbine we are only extracting 45%. Right? How we can optimize it? So as we said, we reduce the energy content of the steam coming out of the turbine, but we are at 70 degrees. So what's the boiling point of water at 1 bar? 100 degree. So 70 degree, it means we are already under vacuum. Right? And here, but there is a limit. Another way is you put in more energy at the inlet. So you go at 500, 600, here you could see efficiency is going up. So this one stays same. We assume flue gas is coming out at the same temperature from the stack, and we are just varying here this superheated steam temperature. So the same So what we are doing here, we are burning fuel. Chemical energy of fuel is transferred to the thermal energy, to the steam. But what we can do, instead of using fuel which contains a lot of carbon, we can use nuclear reactor and harness nuclear energy. So the whole rest of the whole cycle is similar. It's just the thermal energy supply medium is different. In earlier case, it was burning a carbon-containing fuel. Now it's the nuclear reactor. So there is another way of generating electrical energy is hydro. Hydro share in the overall electricity mix in India is a little bit higher than the global average, because we are blessed with a lot of rivers, and we are also blessed with the advantageous terrain. You just you don't have to have rivers, but you also need to have terrain that you have some slope. Here you could see, basics of hydro generation everybody knows. But as I was saying, we are blessed with such a terrain that at certain 200, 300 meter we have higher level, and then at 200 meter later we have lower level, so that we can make use of this potential energy difference, make a dam, stop the water, and have the controlled flow of water from high level to low level. By this you turn the turbine and generate the electricity. So other two methods up to this point is similar. It's just the energy is not transferred by steam, but it's water, and it's not the thermal energy, but it's the potential energy. Now comes the sun. So the global solar radiation, how much solar radiation we receive at ground level. So global average is somewhere around 1300 watt per meter square. But the problem with solar is it's not shining 24 hours a day, 7 days a week, 365 days a year. But if you have natural gas, you can burn it 365 days a year, 24 hours a day, 7 days a week. So it's continuous supply of energy. Extract natural gas and have continuous supply of energy. That's the problem with solar energy. It's only, you could say daily 12 hours of daylight, night time, but there is also a disparity between locations. Once again, in India we are blessed with more sunshine than some other countries. So if you go to Scandinavian countries like Norway, sun rises somewhere around 9 a.m. and it's already dark at night. It's only 6-7 hours. That's in winter. But we have year-round sunshine. But we have year-round sunshine, and some other countries like Middle Eastern countries, South American countries, they are also equally blessed. Some countries even better than us. So if you look at the potential, you could see the solar to electricity generation currently is somewhere around 20%. So the solar PVs what we have nowadays, the efficiency is somewhere around 20%. And a lot of research is focused on increasing the efficiency of solar PVs also. Now, if you look at the whole land mass we have, leave 70% for ocean, which is a good number. So only 0.4% of remaining land mass is required for total worldwide. Do some maths based on 1300 watt per meter square. And out of this remaining land, 0.4% land, if I leave 35% of forest land area also, only 0.6% is required to supply the energy demand of the whole world. Then there is wind. So we started with coal or natural gas, the steam cycle generated power. We went to the nuclear, hydro, solar. So we're just looking at each and every source of power generation. So that's wind. So we all know that the specific heat of soil is much lower than specific heat of water. That means, and God's sun is not distinguishing between sand, soil and water. So the solar radiation is similar. That means for the same amount of energy hitting the ground and hitting the water, the water will be, let's say, will be at lower temperature. So similarly, the temperature of the air over the water is lower, and that creates a density difference and a natural dark, which later on turns into what we see as wind. And this energy, this kinetic energy can also be harnessed. So once again, like hydro, it's the potential energy of the water due to the rate difference. This time is the kinetic energy of wind, which is used to turn the turbine and generate electricity. So there was another way of, or there is another way of harnessing the sun energy directly as thermal energy. So you generate steam via thermal energy absorbed from the sun, and once again turn the turbine to generate electricity. From the sun, the first one was about the thermal energy, but thanks to the invention of PVs or electromagnetism, you can directly convert the solar energy into electrical energy. That's the even much efficient way of generating electricity from sun. So coming back to the first source, here we had the coal. Here we had coal. If we replace this coal with biomass, we could apply the same cycle and generate once again electricity via steam cycle. Okay, then there is another way of using biomass. Instead of having this thermal cycle, you can have the bioconversion to some fuels like bioethanol. You use biomass and convert into a suitable fuel like ethanol. I think this we already discussed. There are so many hurdles moving from conventional to away from conventional energy sources. So I think this we didn't talk about. Oil and coal-based power generation, this society has been doing for last almost 100 years. And it's a very well established technology. Oil and coal still has abundant supply, there's a lot of reserves still available. So it's also once again the political aspect into this. To promote the green energy and to promote energy transition, people are saying we do not have oil left, but fact is there are still a lot of oil reserves and gas reserves left, even coal. So as we were talking before lunch, so societal inertia, personal inertia, there is also economy of inertia. So who will pay for this extra cost? I've been doing this for years, so I'll continue to do this. Difficult to convince people, society. Cost of power generation still favors oil, coal. We saw already the economics, 174 versus 79 euro per megawatt hour between natural gas and coal. So who will pay for this extra cost? Supply chain resources issue. So these are new technologies. That's true. Uncertain geopolitical environment. We are living in a world where we have so many fights going on, war going on. I think 50 years back there were more alignment, the governments were more aligned than today, so that's also. We touched upon the nuclear power. There are also, nuclear power is a very let's say, potential clean energy source, but there are so many risks associated with nuclear energy. Just to mention some of them, accident is a big thing. Japanese accident has really scared many governments, and most of European governments have already decided to shut down all their remaining nuclear plants. Okay, I think this we already saw in the morning. There's nothing new, but I wanted to cover that. So this we just started to talk about this disparity into solar energy available. So here you could see we are somewhere here, and in the region of 2,400 to 3,000 hours every year we have bright sunlight. And just compare this with this region, which is Europe, Northern Europe, some parts of Russia, you are even below 1,200 hours per year. So this is just to show the perspective. There is a disparity in solar energy available worldwide. Now let's do the calculation what we did in the morning for these two locations. For these two locations, one where we have 2,500 hours. 2,500 hours per year, like India or some other country. And on one location we have 1,200 hours per year. So capex of the solar panels is, for sake of simplicity, I assume similar. And as we were discussing in the morning, the capex, the money you spend, you have to pay it back. So we use normally a small factor, capex factor, 14%, that based on the rate of depreciation and the interest rate what you assume. But based on these assumptions, you could see that at one location using the same energy source, I have the electricity price 174, on the other one 84. So huge dependency on the location. So one can say, okay, let's produce power at this location and transfer it to this location where you do not have so much sunshine. But the problem here is we have a lot of transmission and distribution losses. So it can add up to 8%. And this number is for certain, if I remember correctly, some 1,500 kilometers or so. But as you go intercontinental or interstate, you can have almost 30-40% loss. So whatever you are generating at one point, almost 40% is lost before you receive it on your receiver end. And here you could see the transmission losses. That depends also on the population density. So if you have high population density, you do not have to travel so much. So your losses are low. So high population density, lower losses. I don't see India here, but we are also somewhere in this region. So higher losses. So the one issue with the solar is disparity into solar radiation based on the location. Another one here you could see, and that's a major issue, over the daytime. And these are the plots showing energy consumption over the daytime. So from midnight till midnight. You could correlate it in the early morning hours. Let's say until morning hours, the energy consumption is very low, and then it's slowly going up, and then it stays. And in the evening times, slowly going down. Right? And that's the power production if you install a solar PV. So during this period, you could see there is no solar power generation, but there is some consumption. And in this period, you could see there is a lot of solar power production, but there is not so much consumption. So during the day, 0 to 24 hours, at certain point, a time you are producing less or you are producing nothing. But at certain point of day, you are producing much more than what is required. So that's also an issue with the solar energy, which we call normally intermittency issue. So this power is supplied not continuously like in a natural gas-based power plant. You can run it 24/7, 365 days a year. Here you can have power intermittently. So that's the intermittency issue what we have. Now how we can solve this problem is with hybrid solution. So what you can do, you can have a natural gas based power production and the solar PV based power production, right? So during this period when you do not have any solar power production, you turn on your natural gas power plant and generate power what is required. But what you will do with the additional power generated during this period, because you could see here you have much more power production than what is required, right? So here you could see we had the same natural gas based power plant, you have the fuel, the gas turbine, steam cycle together, and then you, on the steam cycle, you add the solar electricity. Right? So we said when we do not have solar power, we can generate power via electricity, via natural gas, right? And during this period when we are generating more, we can store the energy in batteries, right? So this one is hybriding natural gas power plant, solar PV, and even the battery storage. So combining solar and say fossil-based power generation, so synchronization of supply-demand solution for intermittency problem. These are expensive. Well, you could imagine if we have only natural gas-based power production, you just install this much capex. But if we have hybrid solution, you have to install capex for solar power production, also for the natural gas-based power production. So, of course, your capex is much higher. So that's what we have here in point number 3. High capex compared to standalone NG-based power production. So reduced CO2 emission, pure solar means no emission, but during the time when you are running your NG-based power plant, you have some. So you can have from 0 to 1 with the pure solar-based power production, up to pure natural gas-based power production, something in between, based on the ratio of power supply between these two sources. Solving this intermittency issue using battery, that's also nowadays gaining momentum. But the problem with the battery is the loss of, let's say, it deteriorates the economics, so losses. And we are talking about losses not in terms of weeks or months, but in terms of hours. So whatever you store in your battery, you will not get the total power even next day. So full battery and solar power, that's I would say still far away. And a lot of research is focused also on increasing the efficiency of solar. So we saw at the moment it's somewhere around 20%, and you could imagine increasing it by 2%, you suddenly increase the power production by 10%. So 20 to 22, it's only 2% in terms of efficiency, but the power production will suddenly go 10% higher. So a lot of focus is also currently on increasing the efficiency of solar cells. So that's the future perspective. IPCC and all the governments have kind of agreed. So 70% of power by 2050 will come from renewables, mainly from solar PV and wind power, and by 2070 almost 100% of power will be replaced by solar or wind renewable. So currently we have only 20%, as I said, pledged by major economies to reach 100% goal by 2070. So solar, PV, wind, they all will play a major role. Hydro continues to grow. Space it growth historically. We already discussed for nuclear there's a mixed approach within the society, within the countries, within the community. So march towards the global goal instead of national program. So it's more collaborative state effort. Focus on smart grids, energy storage, new materials. Those are the say, focus area. So far we talked about electricity. So major part of the total energy use is for electricity. That's what we talk about now. And that's for the transportation, where you could see majority of the transportation energy use is within the public, say light duty vehicles. And another big share is the freight transport. And somewhere here is the water transport, air passengers, and where all this energy is coming from. So majority of this is coming from crude oil, basically via gasoline or petrol. And then the heavy distillate, that's the diesel, jet fuel, aviation turbine fuel, natural gas, compressed natural gas, that's also. Here you could see which mode of transport is how much polluting. So that's per kilometer, I guess per kilometer per person, and the air transport is somewhere around 255 grams of CO2 emitted. And look at the train compared to 41. So yeah, sure. Question?
Flight is taking time.
Yes. But intercontinental transport, we can't avoid this mode of transportation. So now, probably you all are already aware, and even in India we have so many EVs nowadays. So countries are already moving from gasoline-based passenger cars to electric vehicles, and here I'm just showing how this rapid growth occurred in last 4 or 5 years. Look at the graph, exponential growth over the last 5 years. And on this front, China is actually leading. So look at the graph or the exponential growth China had compared to some other countries. Once again, electrification country-wise, you could see that's the plug-in electric cars in one per 1,000 people, and here you could see Scandinavian countries are much ahead of others. So rapid growth in last 15 years, but the issue here is capital cost is still higher. So buying an electric vehicle is still 20% more than buying a similar gasoline vehicle. Government subsidies to promote EVs. So even if you can buy a EV here at today with 20% higher cost, the problem with you will be the infrastructure. The range is small and the infrastructure is not there, so you will not find the charging points. It's getting better every day, but still infrastructure is not catching up with the rapid pace of EV sales. Early pushback from auto and oil lobby, they will not, so oil lobby or oil industry for obvious reasons, because they don't want to see their sales dropping down. But unfortunately, in the early phase, auto industry was also not so much interested in moving from gasoline engine to battery operated electric vehicles. But now they are coming up, and a lot of new EV models are coming up. Gasoline technology is a mature technology. That's for all kind of transportation or vehicles. And EV has already matured for light vehicles, but not for heavy duty transportation like truck transportation and other things. So we need different solution for heavy duty sector. Electrification on railway is already one example. So hydrogen biofuel cell maybe it's not a good solution for light vehicles, because the capital cost of buying a hydrogen fuel cell vehicle is almost 2.5 times compared to a gasoline vehicle. Operating this hydrogen vehicle is also 2 times expensive. So operating cost is high, buying cost is high, and on horizon not enough hope or possibility of bringing this cost down. So probably hydrogen for mobility is not a very good solution, especially for light duty vehicles, passenger vehicles. So EVs, sorry?
Like two-wheelers.
Like two-wheelers, yes.
Because hydrogen buses are there, hydrogen, IOCL just,
yeah, so on the heavy duty side, it's good, but for the light,
but it's still on trial, because hydrogen refilling stations are still not developed yet.
Yes.
In Norway also, there are not, work is going on.
Many hydrogen refueling stations. Yes. So that's the aspect I touched upon, that the infrastructure is not catching up with the auto industry. So they need to synchronize as well. So we touched upon power industry, we touched upon transportation. Now we look at the industrial consumption. So different form of energy used within the industry. One major is thermal energy, and there we saw it's basically natural gas. So coal is more towards electricity production, but in industrial energy consumption, it's mainly natural gas. Predominantly it's electrical, but also thermal as heat. And electricity, we know, running the pump, running the compressors, and all those kind of uses. Now electrical, we already saw we can replace this electrical energy supply from coal, natural gas to renewable power. So this is already cleaned up. And thermal at various, now thermal energy we need within industry at various temperature levels. So you could imagine if heat is required at lower temperature level, the steam can be generated directly using green electricity, right? But if you need energy at a little bit higher temperature level, you cannot replace it with electricity, because supplying energy at higher temperature level via electricity is much more expensive. So in 20-30 years back, we saw that the efficiency of this thermal power plant was 40%, and that was because of this inherent reason we cannot have condensation within the turbine, and that's why a lot of energy in steam is lost in the condenser. So 20-30 years back, they came up with the idea, especially in Western country where you need a lot of domestic heating. instead of condensing it in a condenser via cooling water, via cooling tower, they will supply this energy for the district heating. So that's a combined combination of heat and power. They call it CHPs. So you do not waste your energy to atmosphere, but you make useful use in domestic heating, thereby replacing natural gas which would be used normally to heat up your homes. So at lower temperature that's easy, but high temperature heat supply, that's a challenge. I think this we already all covers. We talked before lunch that cement is an industry where you need to supply a lot of energy because calcination is highly endothermic reaction. A lot of energy needs to be supplied. Another example where you need to supply heat at very high temperature is syngas production, iron industry. So these are the industries where it's absolutely not possible to replace your conventional energy sources like coal, natural gas and others with electricity. We saw the example of cement, CO2 release from process, that's a challenge. So these are hard to abate industry. Limestone calcination is responsible. So if we look at the CO2 emission from a cement plant, almost 70% is coming from limestone and only 30% is from the fuel uses. Although it's very highly endothermic industry reaction, sorry. But 70% is coming from the process side. And as you said, until unless we find a replacement for limestone, we cannot avoid this 65%. And it's highly endothermic, lot of CO2 within the process, and the optimum reaction temperature is also 1400 degrees. That means we can also not replace this energy supply with electricity. So we continue to supply energy via conventional energy sources. This we already. I'm just speeding up because of so questions so far. Questions.
Okay, I have pointed out some things regarding. Okay, all are here, right? Sir very nicely explained about greenhouse gas, greenhouse effect, GHG effect. Right? So, I think all of you know what is greenhouse. What is greenhouse? House which looks green. Yeah? Greenhouse effect. Greenhouse effect. Yeah? Greenhouse effect. Greenhouse effect. Effect coming from the green sources. Greenery. That is the greenhouse effect. Am I correct? Greenhouse effect. It is a far away process. I mean, greenhouse effect. This is just wanted to clear you all. It doesn't related to greenhouse at all. Greenhouse effect is something which we have plants inside the glass wall. Roof made up of glass. Walls, all the walls made up of glass. Inside there is a plant. Have you ever seen such kind of plantation or heard about this? There is a plantation inside the glass room. Walls, glass, roof, glass. What is the purpose of making of this? Sun radiation will come inside, right? The plant will take and it won't go directly, but it will be trapped inside. So that when there is some lower temperature, then plant can utilize. That is the greenhouse effect. Is it good or bad? Good. It is good to live plant, right? So, okay. This is something about the greenhouse effect which is nothing to do with the green. Okay. Tell me the temperature of the universe. What could be the temperature of the universe? Minus 270. Very accurate. Are you? Okay. Fine. I was about to say something around minus 250, but to be very precise, this is minus 270 degrees centigrade of the universe temperature. But Earth having advantage of what? Near to sun. Near to sun. Okay. Now, see, I'm talking about now GHG gases or something like that. Yeah. So we have atmosphere. What is speciality about Earth? Earth is having atmosphere, kind of blanket. If you have blanket, you will feel cozy, right? There is temperature minus 270, but we are near to sun. Without blanket, if sun directly comes to Earth and goes back, re-emit back to space, then the temperature would have been minus 15 degrees centigrade. How much? Minus 15 still. Is it livable temperature? No. Why? Minus 15 degrees centigrade means ice, there will be no water. Life is not possible. So how life is possible? How it has been, it could have been possible, all of this? Because of CO2, because of methane, because of some of your, industrialization, many years ago I am talking about, right? Something, agriculture or things, right? So what are the greenhouse gases? Water vapor is also one of them, right? CO2, methane, right? CO2, methane. Now I am talking about I will be talking about the climate change, global warming, greenhouse effect. I have told you greenhouse effect. Now moving to the global warming something and climate change, right? What I was talking about? Minus 15 degrees centigrade if we don't have blanket of greenhouse gases. So called now greenhouse effect, without greenhouse effect. Now due to this carbon dioxide, methane and everything, which is the natural thing, due to this we have temperature of plus 33, minus 15 plus 33 would be around, or minus 18 something, plus 15 or plus 18 degrees centigrade, plus 18 degrees centigrade, right? Now this average temperature, somewhere it could be more, somewhere it could be less, right? But the average temperature now plus 18 degrees centigrade. Is it life supporting? Yes. Plus 18 degrees centigrade. You have liquid water as a liquid, right? Plus 18. What makes it possible now? Due to greenhouse effect, which was natural process, now comes into picture why this is become a dirt or a bad thing due to industrialization, due to deforestation. What the forest or the tree does, what it does? It takes CO2, it gives oxygen. But here what happens? Now what is happening? Industrialization produces CO2, lots of CO2, unnecessarily, right? Okay. When sun radiation comes inside the Earth's surface through this, crossing this, blanket as a short wavelength, then these greenhouse gases, they do not absorb heat. They do not absorb because of short wavelength. Then it comes back to hit the Earth surface, then it re-emits. Then the presence in the atmosphere, CO2, methane, everything. Earlier it was not absorbing while coming. because of short wavelength. Now it is re-emitting, then it is converting into the long wave radiation. Now these gases, what it does, it traps the heat. It traps the heat, and heat gives the atmosphere sufficient temperature, which converts -18 to +50. Right? But more and more CO2, more and more methane. Does farming also creates which gas? Due to cow and everything, yeah? Methane, everything, right? Right? So, what it does, it now trapping more heat. Now trapping more heat. What will happen? If it is trapping more heat, then more temperature. What comes into picture? Global warming. This is the normal. All these things were normal. If you, I don't have the live chart with me. If you will see in the internet, temperature above versus the earth. You know, for changing the temperature variation, now I am coming into the climate change terminology, right? Hundreds of thousands of years take to change the temperature. You know, change in temperature to occur 0.8 to 0.2 degrees centigrade. It's a slow process which takes hundreds of thousands of years. Climate change. It's not a new terminology. But over the decades, since industrialization from 1960 something or right, for that decade, point something, I don't remember the exact figure, something say 0.16 or degree centigrade. Change in temperature. So Earth is such a big temperature. You will say 1 degree centigrade. To get 0.1 degree rise in temperature even. You know how much heat will need overall Earth. Can you imagine? It's not about a room. It's not about a small thing. It's about the Earth. Overall Earth. But now, recently in this decade, it happens 0.26 or twice. Increase in temperature. Rapid temperature. Now we were up to 1.2 degrees centigrade. If this will remain so and so, then we will hit the temperature by 2030 to 1.5 degrees centigrade. In 2050, it might go up to 2 degrees centigrade or 3 degrees centigrade. Then there will be no life. There will be no life. Glacier, you know, wherever temperature, this is again a very long subject. I won't go that deep. Right? Understand climate change? Climate greenhouse effect was a natural, but we human made it, you know, excess, something bad, right? Again, climate change was nothing new. It was happening from hundreds of thousands, slowly. But now, why? Because of greenhouse gases and trapping the temperature, and ozone layer, breaking of ozone layer, coming into UV radiations and everything. That increasing the temperature. That is what? The climate change, rapid change in temperature. So it is a dust. It is a point of consideration. Now, one last I want to touch. Global warming potential. So sir has nicely explained one of the slides. Global warming potential. Carbon dioxide is having 1, right? We have taken it as a reference. But see, the global warming depends upon 2 factors. How long the gas stays in the atmosphere and what is its global warming potential. So carbon dioxide stays in atmosphere for hundreds of thousands of years. But methane stays, say, at 10 years. Other hydrocarbons or other F-series gases, sir, that is the hydrofluorocarbons, which is HFCs, hydrofluoro, which is comes from the human activity. I mean, like refrigeration and everything, refrigerants, right? So there's just more, lesser. Now, but what is the point here? Methane has a global warming potential of 23-28, right?
Yes, 23.
What is global warming potential? Now, methane has a potential of what? Warming or trapping the heat 28 or 23 times more than CO2. What 1 ton of CO2 can does, equivalent to 23 times more. Only a single ton of methane, 23 times more. And something, sir, kitna? 256 or something for hydro. NOx, 253 times more. So that is why, or even all these things, global warming potential. Now, see, in trading or in currency, what we have, the unit as a rupees. So in this carbon market or in this trading system, what we have, evaluation and calculations. There is GHG evaluation, GHG calculation, GHG inventories. All these terminologies are there in the more bigger picture. Tons of CO2 equivalent. The unit is tons of CO2 equivalent. So you have to say what is the amount of CO2 and what is its global warming potential multiplied. What is GWP of CO2? 1. Whatever amount is this, it will be tons of CO2. Whatever methane is there from your industry or something, amount in kgs, multiplied by its global warming potential, which is 23. That will be equivalent to tons of CO2. Like NOx, whatever amount of NOx and its global warming potential, something 256. Multiply is equal to tons of CO2. Now all quantities of, your methane, NOx, FCX, whatever gases are there, water vapor, all global warming potential values, you have converted into ton of CO2 equivalent. Now you have overall sum of ton of CO2 equivalent. Yeah, this was more broader picture about the global warming potential, which will come more into clarity further if we have the sessions for the GHG evaluation, inventories. This is a big picture. That's what I want to say. 4 topics I need to cover, just to touch. Thank you.
Thank you very much.